Sandra Leclerc, who will tell us about UV completions of about deformations of CFT.
All right, thank you. Okay, thank you. Okay, well, it's a pleasure to be here. Never been to Berlin, and it's been exposed to some interesting work in this vibrant community. It's my first time participating in these kinds of conferences. I was actually trying to decide what to talk on. There was two possibilities. The titles Integrability, Duality, and Deformations. So in the past year, I exchanged a lot of emails with some of your friends here, Svetos and Siampos, and they kind of helped me out on a problem I had been working on for quite a long time, which would fit under integrability and duality. The simplest integrable model is the Sinch-Gordon model. And surprisingly, it's not fully understood. And it has a duality, but it's not clear that, it's a strong to weak coupling duality. And it's not clear this analytic continuation actually makes sense. So I think a lot of people in this audience could help out with that. So that's not what I'm going to talk about, because I don't think that this issue is fully resolved. So instead, I'm going to go with integrability and deformations. Okay? No dualities. Okay. So it's based on just recent papers I wrote last year, and more recently I collaborated with Shamgrim on this paper, which is accepted in JHEP. So what is the problem? The problem is very general. Let me remind you some basic features of the renormalization group. So I'm going to formulate it in terms of an action. So I'm going to assume I'm given some conformal field theory. And then I start perturbing it with both relevant and irrelevant operators. Now, the standard law is essentially correct. At low energies, you can neglect the irrelevant operators. That's why they're called irrelevant. For example, in studying the standard model, we don't have to look at quantum gravity corrections. Those are all irrelevant perturbations. Okay? But if you're interested in very, very high energies, then it's the irrelevant operators that completely determine the physics, determine the ultraviolet properties of the model. Right? There's a crossover region, which I won't really be interested in. So the fundamental question is the UV theory well-defined and finite? I mean, this all beyond standard model physics is basically trying to address this question. What is the high energy theory? Is it a string theory? Is it finite? Just pure quantization of Einstein's action? We know that's not defined in the ultraviolet. So first we have to see if the UV is well-defined. And then can we reconstruct it? More interestingly, can we reconstruct the UV theory from limited information in the infrared? Like for example, we have the standard model, view that as a low energy theory. Just knowing the information that we know about the standard model, can we figure out what the ultimate UV theory is? And in general, the answer is obviously no. I mean, well, one way to formulate that is because of the C theorem. C theorem tells you that in the flow from the ultraviolet to the infrared, there's some degrees of freedom are lost. But so we could stop here, but I'm going to provide a lot of examples where the answer is yes. Okay, we can reconstruct the UV theory. So this is central to, well, I already mentioned standard model, quantum gravity. Within the context of quantum gravity, there's a set of ideas called asymptotic safety. Like maybe, for reasons we don't fully understand yet, maybe quantum gravity, I mean, Einstein's theory secretly has some fixed point in the ultraviolet, and you don't have to worry about ultraviolet divergences if there's a conformal fixed point. And it's also connected a little bit with the swampland. Swampland, that notion was born in string theory. I mean, suppose you have a low energy theory. Does that theory come from a string theory or not? So that's essentially the same question. Maybe there is no ultraviolet completion of some low energy theories. Okay, in that case, it's the context of string theory. But the same ideas will apply here. So, like I said, we have to limit the scope here. So I'm going to be only in 2 dimensions. That allows integrability. Then I'm going to, so I want to look at this, the perturbation by irrelevant operators. So I'm going to the very high energy limit now. So the irrelevant operators are the important ones. I'm going to take the leading irrelevant operator to be TT bar. Many people here are familiar with this kind of thing. T and T bar are the left-right components of the stress tensors. This is a dimension 4 operator. That'll be the leading one. And then I'm going to consider adding some higher irrelevant operators. How to do that was described by Smirnov and Zamolodchikov. Essentially, if the theory is integrable, well, every theory has a stress tensor, okay? But if it's integrable, there's higher dimensional versions of the stress tensor that define local integrals of motion. Okay? So they all have integer spin. And from that, you can construct the analog of TT bar. Right? So TT bar 1 is TT bar. Okay? S here is an integer, typically an odd integer, but it depends on the model. And the dimension of these operators is 2 times S plus 1, so it's an integer, higher and higher dimension. So this is the model I'm looking at. Some CFT, and then I'm going to perturb by all these higher TT bars. Okay. So a probe to see whether the ultraviolet is well defined is to consider the ground state energy on a circle of circumference r. In stat mech, that would be 1 over the temperature. And so the ground state energy, it's conventional to express it in terms of a scaling function, C of mr, with this coefficient. And C, well, if the theory was conformal, C would be the Virasoro central charge. Okay? But if the theory is not conformal, it tracks the RG flow. Okay, so this is a function. This should be defined in the infrared and ultraviolet. It should be defined for all scales if the theory is fully well defined. And this is kind of obvious. Infrared limit is R goes to infinity. UV is R goes to 0. Okay. So pure TT bar is very interesting, and many people in this room, I'm sure know this, but let me remind you. So I set all the higher TT bars to 0. So there's one coupling, the leading one. Then it turns out the ground state energy is universal. It satisfies a Burger's type differential equation. Anyway, I like to write it in this form. Okay, so here you're given, these infrared central charge as a function of the scale. Little r here is a mass times big R. H is a ratio. This is dimensionless ratio here. You have that one coupling, alpha 1. And the interesting case is alpha 1 negative, so H is positive. And then eventually, if you just plot this as a function of R, you're going to hit a square root singularity. Okay. So if this is it, there's a sort of shortest possible distance. You can't go to the full ultraviolet limit. Okay. So this is the kind of picture you have. Okay. Wait, I think this is the slide I wanted. So there's 2 interpretations of this. The original TT bar, I think, was mainly the first interesting papers were in the concept of string theory. So there R star is a string scale, and that square root singularity signifies some kind of Hagedorn transition. And everything's okay. It's a string theory, okay? Which is kind of an ultraviolet completion of some kind. But if you didn't know about string theory and you were just a quantum field theorist, this is not good. This is the usual folklore that if you perturb by irrelevant operators, you start generating more and more irrelevant operators. And the whole theory is out of control, and it's unpredictable. Okay? So the question I pose is, can we somehow tune, so let's add all these other irrelevant operators, and can we tune these couplings to cure that singularity in such a way that the theory is fully defined in the UV? And can we actually, there's a classification problem here. Can we classify the possible UV completions? Okay. So this is the picture. So the x-axis here is 1 over r. So the infrared is r, 1 over r equals 0. Infrared is 1 over r is 0. That's up here. Now the leading perturbation is TT bar. So any possibility here, they all look the same around here. But depending on what the other higher irrelevant operator couplings are, these things, they start to change. And maybe there's still a singularity. But I'm interested in the ones where there's no singularity. And I'd like to classify the possibilities here. Okay.
When you say that you want, I guess if you when you say that you want to fuse the deformation, you mean that you want to fuse the initial condition of this differential equation? So like the initial choice of operators, or you
No, once you add
particular flow?
once you add the higher irrelevant operators, you don't have this differential equation. There's no this Berger's differential equations.
There is another flow equation.
Yeah. What I'm going to do, I'm going to use the TBA to track the RG flow.
All right. Okay.
Okay, that's going to be the main tool. Okay, so these are the steps that I would have to follow here, that we try to follow. So first, we're given the infrared conformal field theory. Okay, assume we're given that. First, you want to look at all the possible integrable relevant perturbations of this theory. Once you do that, for each of those possibilities, that determines a low energy spectrum. Okay. And you know the S matrices. Then we turn off this relevant operator and get a massless theory. So this gives us a scattering description of the conformal field theory. We heard about this yesterday in Torelli's talk. So for each possibility here, we have a set of left-left. So L here is left, R is right. There's a set of left-left, which are equal to the right-right scattering S matrices. It's very well known that if you only have left-left and right-right scattering, the theory is conformal. So we have a scattering description of the CFT. If there's left-right scattering, then that would break the conformal invariance. Okay, so here left-right is trivial. Now for each of these choices here, you turn on the higher irrelevant operators. This breaks the conformal invariance. So the left-right now becomes non-trivial. And it's known that it corresponds to a CDD factor. Okay, I think people know that. I forget what C stands for Castellano, but D is Dalitz and the other D is Dyson. Now, I continue the steps. Then we use the thermodynamic beta ansatz as the main tool. And we require that there is a well-defined central charge in the ultraviolet. So the scaling function is valid on all scales. Okay. I'm also going to require this ultraviolet central charge to be rational. It's hard to justify that exactly, but it turns out if it's rational, there's a better chance that we can identify what that conformal field theory is. All right. For example, in some cases, it seems that everything's well defined, but the UV central charge is less than 1, and it's irrational, so we can't even identify that with a minimal model. Okay, so we know that theory doesn't even exist, but somehow, well, I don't want to focus on that. And we're going to restrict to diagonal scalar theories, sometimes called reflectionless, meaning that if two particles, you have particles of if this signifies a particle of type A, then A scattering with B produces A and B's, not C's and D's. Okay. For the Sine-Gordon theory, for example, is not diagonal. The solitons, there's a U1 charge, and there's a reflection of stuff, so this is not necessarily true. So anyway, this is mainly for simplicity. Okay. So I think the most interesting example, which is the one we worked out in quite a lot of detail, is just the Ising model. It's probably the simplest conformal theory, right? And in the first step, it turns out there's two integrable perturbations. First one is kind of trivial. This is our conformal field theory. We know this has a Majorana fermion description. There's two primary fields. One would just correspond to adding a mass term. Then we set that mass to 0 to just get the conformal field theory. Then we start adding TT bar. But in any case, this is the simplest case because this is a free theory. So the left, and right S matrix is just -1. The minus is because it's a fermion. And well, we're going to, this case, we could definitely classify the possible ultraviolet fixed points. Kind of more interesting is that the other primary field is a spin field, and it turns out that this is also integrable, as first shown by Zamolodchikov, late 80s. And it involves 8 particles, nothing to do with the Majorana fermion. So you have 8 massive particles here related to E8. I'll explain that later. So back then, people completed the bootstrap, especially people up in Durham. And so the left, and right S matrices are known. But they're kind of complicated, right? I mean, there's 8 particles. So there's 64 different S matrices, but it's all known. I'm actually not going to need the exact form of these guys. So, but given those left, and right S matrices, now we have to consider the CDD factors. This wasn't really in the literature before, not quite in this way, because, for example, Smirnov, Zamolodchikov, they were focused on the massive case. So there, the CDD factors were exponential of I sinh S theta, okay? Where these dimensionless couplings are just proportional to the original couplings. For example, G1 would be alpha 1 times m squared, which is dimensionless, okay? But I realized early on when I was looking at this problem that you had to factorize the sinh into e to the plus s theta and e to the minus s theta and identify them right left versus left right left. Okay, that made the TBA converge. Okay? But anyway, if you look at this form, you can see that it satisfies this is essentially the only identity that these guys satisfy. Right? It's like a kind of unitarity relation. Okay. So, but this previous form is a little hard to work with. In general, what's in the exponent here this doesn't converge. So I want to work on a slightly different basis. And this is based on a pretty famous paper of Alyosha Zamolodchikov. Let me consider the center mass energy for left with right scattering. So here, this theta here, so it's just m squared e to theta. This theta is the difference of the two rapidities of the two particles. And Zamolodchikov proposed this kind of form for the S matrix. We saw this also in Torelli's talk yesterday. Now, if there's many particles, it's quite straightforward to see what the generalization is. It looks like this, okay? And how the masses appear here is such that you can check that if this is pure TT bar, only the lowest one, then this reproduces the results of the Berger's differential equation, et cetera. So that's where this tells you where you should put these masses. Okay. And it turns out you can match. So originally I wrote down Lagrangian in terms of these parameters alpha. You can explicitly relate those parameters to these mu's. I'm not going to give that formula, but you can definitely match these two expressions.
So those mu are satisfy some sort of triangular relation as well, or they're just fixed?
Can you repeat the question?
Those mu's,
Yeah.
do they have to satisfy some sort of triangular relation, or they're fixed just by?
There's some consistency conditions, yeah, which I'm not writing down. Because remember, we're trying to fine tune all these alpha couplings. So that fine tuning involves some identities, yeah, that are, yeah, they're sort of triangular. I'm not writing them down here, but we can match the two descriptions. So we can relate these parameters to the Lagrangian. So the convenient form we found, well, if you look at this particular ratio and define a beta, this is dimensionless here, then, so these CDD factors, the basic building blocks is this tanh. Okay? And depending, you could have many factors, so with different betas. So JAB here, big JAB is an integer. So that's the form of CDD factor we're going to consider. Okay, now since the equations are getting longer, I stop writing. So the TBA equations are quite well known. So this is not new. You have these so-called pseudo-energies, and they satisfy an integral equation. These big L's are log of 1 plus e to the minus epsilon. There's the left and the right one. These are the source terms, driving terms. This is just comes from the, if there's no interaction, this is just the energy. Okay. And once you solve the integral equation, which you have to do numerically, okay, then there's a simple formula for the ground state energy. And from that, I can get the central charge, effective central charge. Okay. So that's the main tool. These kernels are derivatives of the log of the various S matrices. Okay, so there's two types of kernels, one for the left-left, one for the right-left, both given by minus I derivative log S. And they appear both, the left-right and the right-right appear in the integral equation. Okay. Okay, so here's one example. I'm not even telling you what the spectrum and everything is. This is one example we looked at based on SU3, which is actually, this is a perturbation of the three-state pause model. Turns out the infrared central charge is 4/5. I'm showing this because this is a plot of this L function, the log of 1 plus that. And you see how it forms a plateau here. Okay, this is not quite a robust plateau. It's a different case corresponding to the maximal central charge. But nevertheless, even though there's not a plateau, you can extract the UV central charge from values of this plateau. And the formula works even if you have a profile like this. Okay. So here, I want to extract the ultraviolet central charge, if it exists. All right? So I have to look at the integrated kernels. So I'm going to, these little KABs are the integrated kernels for right-right and left-left. And then the K-hats come from the kernels for right-left. Okay, so they're not equal, right? And let me define X hat to be e to this the pseudo energy. Right? So turning on in these flat regions, the integral equation becomes algebraic, and it's a relatively simple form. Okay. So you see, if I turn off right-left scattering, This is still non-trivial. And from the solution of this equation, you can figure out the central charge. In that case, it would be the infrared central charge. Then you turn on k hat, solve the equations again that should determine the ultraviolet central charge, if there's a solution. Okay, there isn't always one. So it turns out that this tanh was useful because the integrated kernel is always 1/2, no matter what the beta is. Okay. So for each CDD factor, this k hat, well, there's big JAB of these factors. Each one gives 1/2. So k hat AB is just this. They're all half integers. And it's going to be convenient to arrange these integrated kernels into matrices, big K and k hat. So remember, this one comes from right-left scattering. This comes from the conformal theory, left-left scattering, right-right. And then there's a very nice formula for the central charge. There's a version of this formula in Alyosha Zemlyakov's paper, but we generalized it to a more general situation. This LR here is so-called Rogers dilogarithm. It's the dilogarithm, standard dilogarithm plus a log term. Okay. So it's relatively simple. So if you find the solution to these x hats, this plateau equation, you plug it in and you see if you have a sensible central charge. Okay. So before turning to a specific model, there's some very generic cases. Okay. So it turns out if there's too many CDD factors, there's no solution. Okay. We call that the saturation point. And that's going to give you the highest possible ultraviolet central charge. Okay. And you can see it's quite easy. I mean, without even specifying the S matrices and these matrices K, you know, if K hat set, well, let's call it K hat 0. The 0 refers to this would be the saturation point. If K plus K hat is 1, then you can see that all these X hats are 0. And that's the maximal central charge, because remember, the epsilon has to be real, right? And so the lowest value it could be is minus infinity, and that's when X is 0. But you still have a non-zero ultraviolet central charge, and it turns out to be always the maximum one. Okay? So in this limit, the maximal UV central charge, turns out, I'm going to look at theories based on Lie group G. But in any case, it's quite general here. It's twice the number of particles minus infrared central charge. It's kind of a nice formula. In the models I'm considering, based on Dynkin diagrams, the number of particles is just a rank. Okay. Another generic solution I call diagonal, where instead of this equal to 1, just equal to 0. So now K hat is just minus K. Remember, we know K. K is given by the left and right S matrices for the conformal field theory. So those are all determined, okay? We're trying to find K hats. If you just take this very simple choice, then all the X hats are 1 instead of 0. And you still have a well-defined UV central charge. This case is just the number of particles minus the infrared central charge, which turns out to be the central charge of this coset. I'll explain this notation later. Well, GK is the Westermina-Witten model at level K. Okay. But I'm getting a little ahead there. So let's look at the Majorana case, the fermion. Well, let's look at Ising. Try to do all of Ising. So let's start with the simple Majorana spectrum. Okay. The integral equation is quite simple, because there's no left or right kernel, but there is a non-zero left-right S matrix. So here, there's only two cases. There's only two ultraviolet completions. You can have one of these CDD factors, one of those tangens, And that's the famous example of Alyosha Zemlyalikov. This scaling function is defined everywhere. The ultraviolet central charge is 7/10, which is tricriticalizing. You can have two of these CDD factors. That's the saturation point. And that C is 3/2. Okay? And the interesting thing here is that, well, so far this is what we have. We started at 1/2, okay? One CDD factor gives you tricriticalizing. The other one is C equals 3/2. I found that last year. I didn't know what that theory was. Then talking with Shangram An, my current collaborator, it turns out it's the super Singe-Gordon theory at the self-dual point. Okay. And the 3/2 is a central charge of one fermion plus one boson. It's also supersymmetric. So there's only two completions for the Majorana fermion, and they both have supersymmetry. Oop. I mean, that's kind of good news for the SUSY community, who loves supersymmetry. Here, we didn't put supersymmetry in. Why is the theory massless? We have a massless flow. So in the infrared, there's still something left. It's the massless Majorana fermion. And it's massless throughout, everywhere. It's always massless. But it's still not conformally invariant. So there's a UV and infrared central charge. And there, the Majorana fermion can be interpreted as a Agostino for the broken supersymmetry. That's what's keeping it massless.
So I was wondering, this identification of the UV theory, is it based only on the central charge or also some other piece of evidence?
That's a very good question. So since this is our first stab at this problem, we just checked that there's a well-defined solution to the TBA for all scales with a well-defined UV central charge. Okay. And with more work, you can, but it's hard, but it can be done. You can expand around the ultraviolet in a careful way and, for example, figure out the dimension of the relevant operator in the ultraviolet that it flows out of. Okay, so you flow out of the ultraviolet with a relevant operator. It arrives with TT bar in the infrared. But we couldn't do that for all these cases. It was too much work. We're kind of working on it now, but it's a little bit tricky.
Maybe one quick related thing. So, and this is something that I don't know even in the case of the tricriticalizing flow, which is in principle well understood since a long time. Could one in principle look at the spectrum of excited states along this flow and see that it arranges the spectrum of easing in one point, and then it arranges the spectrum of the tricriticalizing? To
my knowledge, that hasn't been done. So what Zemlyalikov did, the best he did in his paper was that, okay, he figured out he had the right central charge, but then he did one more expansion around the ultraviolet, and he figured out the dimension of the perturbation there. And it was what was expected. Okay. But your question is much more refined. These are kind of hard, but studyable. Okay. Okay, but that's not it for Ising, right? Because remember, there's this other description of conformal Ising with 8 particles. So I'd like to review that a little bit. So why E8? Well, after the original work of Zemlyalikov, I wrote a paper with Denis Bernard and Shangram on essentially perturbations of all the cosets and proposed S matrices for that. Okay, so this is going to be one special example. So I'm going to let G here, just a simply laced Lie group, AD type. Here's my notation. GK was the Mina-Witten at level K, just current algebra. And then GK with this bracket, square bracket, is going to refer to this coset. Okay. Now, it's known that if this is level 1, 1, 2, which is that guy, this has diagonal S matrices. Okay. Now, let's focus on the minimal models. Okay. So what I just described in terms of Majorana is this Ising. Ising. There's one. The rank. The number of particles is the rank. SU2 is rank 1. So this is for these groups, this coset for SU3 is 3-state pods. And we did the classification from that case. There's E6, E7, which we couldn't do everything. But I'm going to focus on E8 because, interestingly, both E8 and SU2 have, this coset has central charge 1/2. So they're both Isings, but in a very weird description, appropriate to a magnetic perturbation. Okay. So if I'm trying to classify UV completions, I have to consider this E8. Okay. So then it gets a little technical, but some of this is known. So let me describe the conformal description. Just the left, right S matrices. So, like I said, there's no E8 symmetry, but a lot of the structure can be figured out from the E8 Dinkin diagram. With this labeling of nodes, this is the incidence matrix. Remember, the big K are the integrated kernels. So they're known, because we know the S matrices for this chi. And it takes this form. So you have this funny matrix of integers. But this is known, okay? All right. Remember, the saturated case is K hat 0 is 2 over 2 minus I. Okay. What was I going to say? Okay. So then you start going fishing. Okay. So the big K, which determines the conformal field theory, is known. And then you're trying to cook up some left-right scatterings that have a well-defined flow all the way to the ultraviolet. So it's a bit like fishing. But the constraints are that the elements of this K hat, have to be half integers, as I said before, because integrated kernel for each CDD factor, each tanh gives 1/2. So they have to be half integers. So let's look at this. So the saturation point, the K hat was just, remember, it's just 1 minus K, which is 2 over 2 minus I. Okay. So that's going to give the maximum central charge. But then, since all the elements have to be half integers, you start reducing the number of CDD factors. And here, there's too many particles to do this very, very systematically. So what we did is we took K hat 0, this is the saturated one. And then we took let n be an integer, and we consider this this set of these possible left-right scattering kernels. Okay. Again, a matrix of integers. Right? The K hat 0 is this. So multiply by n over 2, you get this. So let's just check the conformal case. So if you set K hat to 0, then the UV and the infrared central charge are the same. There's no flow. It's a conformal theory. So there, if you solve the plateau equation, this algebraic equation, you get algebraic numbers. It turns out they're relatively simple. They only involve the irrational square root of 2. And kind of remarkably, if you add up, I had this formula in terms of Rogers logarithm for the central charge, and you have 8 of these guys, kind of funny values, and you get exactly 1/2. Okay. So now we're going to turn on left-right scattering. There's the lowest value. We found the lowest one. Here, this integer n is 1. Okay. Now, the solutions aren't as simple. But interestingly, like 1, so these are the values of these x hats, 8 numbers. And, well, they're supposed to be algebraic numbers, and they are. But their roots to quintic a quintic polynomial. Okay, so this first guy is one root to this polynomial. And kind of remarkably, you plug it into the Rogers-Dye logarithm formula, and you get, with these weird numbers, you get exactly 21 over 22, which is one of the minimal models. I think it's the 9th minimal model. Okay? And this case this is the analog of the Zaimolodchikov tricritical Ising to Ising. Here, because of some older work, we know what the UV CFT is. It's this E8 coset at level 2. So E8 coset at level 2 flows to E8 coset at level 1. And it's a diagonal scattering theory. Okay? And because we know something about these coset flows based on work that I did with Bernard and An, we know the dimension of the operator in the ultraviolet that pulls you out of the ultraviolet. It turns out to be 2 over 11. You can extract that with some work from the TBA. Okay? So that case, that's the analog of tricritical Ising to Ising. Okay? Saturated cases, the maximal central charge. It's not easy to guess this, but in any case, here all the x hats are 0. Here n equals 2. That's the saturated case. Turns out it gives a UV central charge of 31 over 2. Okay. And that we can identify also. It's not the coset, but it's the E8 current algebra. Westermina-Witten model for E8 at level 2. It turns out that has that central charge. Diagonal case is interesting. Again, infrared is always 1/2. It turns out to be 15 halves. And this we have a proposal for what that theory is. What is this theory? We just note central charge. We believe that it's if you take the current algebra GK and you mod out by a rank of U1s, you get something referred to as a parafermion. This is not the ZK parafermion. It's a non-abelian parafermion that depends on the group. Okay. So we identify that CFT as PF2. Okay. And it has that central charge. Okay. So thus far, this is what we have. We have at least 5 UV completions. And here they are. Now, are there more? Well, we kind of ran out of steam a little bit because you have this big matrix of integers, 8 by 8, and you have to start lowering these integers to lower the central charge. And if you just do a random choice, usually there's no solution and no ultraviolet completion. So that would be kind of in the swampland. Okay. I mean, the S matrices are defined, the kernels are defined, but there's no solution to the TPA. So there's no ultraviolet completion for certain types of CDD factors. But probably we could probably write a clever program to sort that out. But we stopped here for E8. We were happy with at least 5 completions. I believe there's more. And the reason I believe there's more is because we looked at some simpler cases. Okay, so replace E8 with SU4. Okay. Now, there's only 3 particles. So it's feasible to do a classification. Remember, K is known, the S matrices are known, so the integrated left, right kernels is known. Here it is. This is the K. So, what we're going to do, remember, the K hats have to be half integers, and because of the symmetries, there's only 3 independent integers here, N1, N2, and N3. So what we did is, well, now it's not so bad. There's only 3 integers. So it's easy to to scan through the possibilities because the saturation point, by the way, the infrared central charge here is 1. Okay. But it's easy to go through this by hand, do one case at a time, because the saturation point is such that these ends can't be any larger than 2 or 3. I forget. I'll show you in the next slide. So here we scan all possibilities. Okay? Sometimes there's no solution, swampland. Okay? But the solutions we found was quite rich. And here we believe this is a complete classification for this case. Okay? And this is what we found. So here are these integers, n1, n2, n3. Okay? So if they're all 0, that's a conformal case. So CUV equals CIR is 1. This is the SU4 coset at level 1. Okay. Then we found all these cases. I guess the largest integer is 4. Okay. There's no more after this. Okay. Some of them we could identify. Some we couldn't. Okay. So let me look at this one. So this is the analog of tricrystallizing to icing. So again, these are irrational numbers, but they're algebraic. They're actually solutions of a cubic polynomial. But you plug it into the Rogers dialogagram formula, and you get a CUV of 11/7. And then we checked in all cases that we're not just doing the plateau equation, that we look at the actual S matrix, plug it with the actual kernels, and solve numerically the full integral equation, and see that it's a nice flow. Okay. So this we identify as a SU4 coset at level 2. Okay. Then this one is an analogous to the previous case. It's parafermion, but parafermion based on SU4. This is the diagonal case. This is called the minimal case. The other ones, we don't. Okay, the saturated case we understand. Okay, this is not the coset, but it's just SU4 West-Winnie-Witt model at level 2. So the maximal central charge here is 5. This one we believe is this coset, but we don't know yet. And some of these other numbers, the ones that are multiples of 1/5, we don't know what they are exactly. But we completely specified the S matrices. These theories exist. We just can't identify them yet. They're probably related to some subgroups of SU4. Like, for example, we're kind of guessing SU4 level 2 mod SU2 level 1. That has the right central charge here. This one too, this coset has the right central charge. The solutions to the plateau equations here are relatively simple. They just involve the golden mean compared to these other ones. Anyway, so even with 3 particles, there's something like 11 cases here. And there's still, well, we know the central charge. That's all we know is the UV central charge. We don't know exactly what these theories are. So there, you'd have to do what you were suggesting. We have to do further work around the ultraviolet, first of all, to figure out what the dimension is of the relevant operator that pulls you out of it. Then, with that, it gives you some hints of what this theory is. Okay. So there's quite a lot of work still to be done. So, summary, yeah, okay, good. Well, I think it's a well-defined classification problem. There's still work to do, but it seems well-defined. We found some results. It's interesting. This is an interesting issue. For the Majorana fermion, remember the SUSY supersymmetry was actually important because the fermion was identified as a Goldstino. This is sort of from the Goldstone theorem. That's why it was massless. Okay. For these other cases, well, again, based on some work I did a long time ago with Denis Bernard and Shangrim, it was actually in the title, these theories have so-called fractional supersymmetry. So there's, in general, there's in all these flows, there's a symmetry with some fractional spin currents, not 3/2, not supersymmetry, and very non-abelian, but they're known to exist. Okay, and probably there's something going on that is an analog of the Goldstone theorem for these weird symmetries, which would partly explain why the particles remain massless throughout the flow. So I think I have a little time. And so there's, well, I think I've already mentioned some of these open questions. Okay, so one thing, for example, what is this E8 thing? Well, suppose you had an Ising model in a magnetic field, but it was vanishingly small, and you turn on these TT bar perturbations. Maybe that has some physical applications. I already mentioned this, the role of these fractional supersymmetries. Are there more based on this E8? I believe there probably is, but we can't prove it, and we didn't systematically analyze it. Okay, thank you.
So thank you for a very nice talk, and we already have one question, so please.
Thank you for the nice talk. First of all, concerning this classification, you were scanning positive integers. I guess that had to do with a requirement of the y functions not to go negative, perhaps, or something like that?
Well, it's basically because quite generally these the CDD factors are products of this tanh theta over 2.
All right.
Okay, so each of those tanh factors, the integrated kernel is
Would be
1/2.
positive.
But remember, it's the log of the S matrix. So if you have 10 factors, then it's 10 over 2, the integrated kernel.
Okay.
So that was a limit there. So they had to be integers for that reason.
And related to this, if I now wanted to re-express the CDD factors in terms of the TT bar S spaces, I guess I would get an infinite combination, right?
It's infinitely,
fully
it's
a transform of
fine-tuned,
whatever
so it's
that is.
infinitely constrained in a sense.
Yeah.
But we wrote the exact formula in our paper with Shangrun. But yeah, it's a strong fine-tuning.
Yeah, no, absolutely.
Yeah, it has to be in some
course.
sense, right? But yeah, you can relate remember these tanh, the parameter in the tanh was what I call beta, which is the ratio of the mu's to the masses. So that you can then compare with the CDD factor in, say, Smirnov-Zamolodchikov, and then you can make a connection with the Lagrangian parameters. But it's an infinite set of relations, really.
Yeah.
Right, because there's an infinite number of couplings.
Okay.
We have a question at the front.
It's kind of maybe conceptual question. Did I understand correctly that you think that just TT bar deformation by itself
Can you
is in
speak a bit? Is it on? But maybe just speak a bit louder into it.
is it? Yeah. So
yeah.
did I understand correctly that you think that TT bar deformation by itself is ill-defined?
I think it depends what you want to do. I think for string theory applications, it's actually the right thing, right? Because they interpret it as some of the original papers, Dubovsky and these people, I know you wrote some papers too,
Yeah.
we cite you, by the way. The physics is just a pure TT bar, and it has a singularity. And I think nobody's proposed anything about beyond this. It's just singularity. It's because there's some kind of string theory there. But as far as pure quantum field theory, I would say it's not defined. Well, not defined on all scales. Or until somebody figures out how to maybe come up with some proposal for interpreting that singularity probably as maybe an instability of the vacuum. Until something like that is, which I don't think exists yet, I would say as pure quantum field theorist, I would say is not defined. But has no UV completion. It has the smallest possible scale, so you have to stop. Then what do?
Do you know what happens with excited states if you
No.
consider your flow?
No, we didn't, no, that'd be interesting to study these excited states, just like, like-
Thank you.
Maybe I can just ask, so how should I think about the fact that the possible irrelevant perturbations seem to depend on the different relevant perturbations? Is that just a tool?
It's really a tool, yeah. But it took a while to sort that out because it's a little tricky, but you have to keep it straight in your mind. See, we first imagine turning on just a relevant perturbation. And the theory is integrable, so then we in principle know the spectrum and S matrices, okay?
Right.
Then we take a massless limit to describe the conformal theory. Okay, so essentially, in that case, you're actually turning off the relevant operator. But you see, this is the part that you have to keep straight, is that this massless limit is the UV limit, ultraviolet limit of the relevant perturbation,
Right.
right? I mean, you take the Majorana fermion, as the mass goes to zero, that appears in the ultraviolet, right? Because it's very high energies, the mass is irrelevant, okay? But then that's a tool, then we forget it, that gives us a scattering description of the conformal field theory, but then we view it as a description of the infrared theory.
But so all of these different descriptions of the same infrared
Right.
theory, they describe the same physics at the end of the day. They are just
This-
different descriptions of the same
Yeah,
physics.
they're different descriptions of the same, just say it's a kind of a little bit of a miracle, like this E8 coset and the SU2 coset both have central charge
But
at
you should
half.
be able to access the different UV completions from only from one description.
Right, so turns out like for Ising, there's only two integrable perturbations. One has his E8 spectrum, one is the Majorana fermion. There's nothing else, so that's all you have to work with. For other central charges, there could be many, like a C equals 1, there could be many possible conformal theories in the infrared that have different left and right S matrices. But the way to do it is to turn on a relevant operator to fix a spectrum, then turn it off.
Oh, we have a question over here. Maybe it's not on.
Yeah,
I don't
yeah,
know.
Hello, thanks for the talk.
yeah. Now I can hear. Yeah.
When you classify the SU4 case, in your coset group, in some parts you have these question marks, like it's not fully, it's like there's an ambiguity over there. Can you elaborate on that to understand what is not why those groups are not the...
So basically, for even though there's a question mark, the TBA has a solution for all scales, and from the plateau, and we can extract one piece of information, which is the central charge. See, so there's no question mark here, okay? But if I tell you, look, there's a conformal field theory in the ultraviolet that has central charge 13/7. Then you have to do some more work here. I don't know what theory has this central charge, what this theory is, but I know it exists, and I know it's central charge, but I don't know exactly what it is.
and
It
the-
might be some weird coset of some type, but from what we've done, we don't have enough information to identify these.
And the guess is agrees dimension and something else, or is just, or is that?
Wait, you say that again?
You have some question marks, but you have some guesses, some ansatz like this, for example, SU4.
Yeah, so some of them we
coset
know.
SU3.
Yeah. So some of these we know, like this is no question mark. Okay. That one either, this this known. So there's at least 5 of them here that we have no questions. We know what they are.
Okay, perfect.
Partly based on things that were kind of known. There's some conjectured flows of cosets. So, and then this matches up with the right central charges. So these are, with no question mark, were pretty solid. But the other ones, I don't know.
Okay, I think Dan has a question at the back.
So at the beginning, you restricted to easy S matrices where you excluded, let's say, sine Gordon or something like that.
Right, right.
Is that just to make the TBA viable, or is there some actual obstruction to this analysis in the context?
It's, first of all, we didn't even know this idea would go anywhere. You know, maybe it wasn't classifiable and maybe there were no ultraviolet completions, so it was really for simplicity.
Okay.
But in principle, like for example, suppose you wanted to look at infrared theory that C equals 1 based on the sine Gordon spectrum, say, okay. The TBA equations are very complicated. You know, they have magnons, and they were simplified by Destri and De Vega eventually, but the TBA equations are much more complicated. So it was really just for simplicity to see if this question is interesting or not. But I think we demonstrated that it's a well-defined program. So
No, I
then
was
it's
just-
just very technical to do these non-diagonal S matrices.
Yeah, I was just in case there was like some actual obstruction you knew about. I wanted to check.
Okay, great. I think we've had quite a few questions. We're a little bit over time. So let's first thank Andre for a fantastic talk again.
Thank you.
And then, reminder, photo now, outside the front. Please go straight, and then you can get your coffee afterwards. is settled down, we'll get going with the final couple of talks of today and of the conference. So it's a great pleasure to introduce Jules Lammers, who's going to tell us about the Heisenberg spin chain and its long-range friends with no strings attached. Please.
So thank you very much. So I would like to thank the organizers for giving me the possibility of presenting some of my work of the past years in this community. So as some of you know or may vaguely have realized, I originally scientifically come from this community, although I never really worked in it. But I attended some IGSTs at the start of my PhD, and so it is actually very nice to be back in this community, see some people again, some familiar faces as well as new people in the field, and hear about the progress. So that's been really interesting. For me, I hope to tell you something about something which I think could be interesting for you guys. So it's indeed about a long-range perspective on the Heisenberg spin chain and some related spin chains. So I will really only be talking about quantum integrable models, only at finite length. So those are some disclaimers. No strings attached. So just either mathematical physics or condensed matter if you wish. And this is joint work with Rob Klabbers, with Vincent Pasquier and Didina Serban, who are also in the IPHT in Paris. And it's also ongoing work with Rob, Didina, and our master student, Ayman Toufik. My goal is to show some of the models that I've been thinking about, to show you what kind of structures you can have for long-range Hamiltonians. And they look a little bit different from the more familiar nearest neighbor Heisenberg spin chain that I kind of assume you will have seen, of course. And I will also show that this is actually an interesting, it has various interesting applications, and it's kind of interesting from the point of view of just quantum integrability, because these long-range spin chains have a different quantum integrable structure. So for instance, if you're working on ADS-CFT integrability and you're trying to find a Hamiltonian that is really kind of relevant there at many loops, then this is a type of Hamiltonian that could appear, in fact. So it's actually rather different from some of the other Hamiltonians that you're more familiar to. And I'll also outline some of the kind of tools, algebraic tools that appear in these type of models. So they're quite different from what you see for Heisenberg. And of course, I will talk about the integrability, the deformations, and some dualities that appear there at the level of sort of algebraic level. So I think it's a nice complement to this conference. All right, so let's see. Can I actually go somewhere? It's on. It's pointing. OK, well, I'll just... It just has some lag. OK, so maybe we'll go. All right, so this is some stuff that probably everybody knows, but it's good to make sure that everybody's on the same page. So spin chains, of course, model magnetic materials originally, and it's based on quantum mechanics. Spin chains are one-dimensional models of this type. So we kind of think of a chain of spins. I will only think about spin 1/2 in this talk for simplicity, but you can go to higher rank, for instance. These models may look, not so realistic, but actually they occur in nature. So there are certain materials whose spins actually mostly feel each other in only one direction. So they're extremely well described by a one-dimensional model like a spin chain. And also they can be built in laboratory with ultra-cold atoms and optical traps and all these kind of things. Now, long-range interactions from the last point of view are actually very natural. So if you have atoms, really, they usually interact not just nearest neighbor, but they will feel each other at some slightly longer ranges as well. So they're actually important models for condensed matter physics. And these long-range models have also appeared in string theory, for instance, in condensed matter physics. And some people are very interested in them from the point of view of quantum computing, because if you build a quantum computer with qubits, then again, they will feel each other at longer ranges. So you might want to understand whether these slightly longer range interactions actually really affect what we know very well for the Heisenberg spin chain, right? We have this fantastic model in which we can compute and understand a lot, but it might be special to nearest neighbor or it might not. So it's useful to have a class of models which are longer range, and especially if they're also quantum integrable, so that we have a very nice mathematical structure to really see what the effect of these long-range interactions could be. And right, so that's the general motivation. So here's kind of the big picture which I like to advertise. So this is kind of like a landscape or a panorama of long-range spin chains. It's kind of like a parameter space. I don't claim that this contains all long-range spin chains, but it contains some very important ones. So we have 3 levels, and on the left we have just the Heisenberg XXX, XXZ, and XYZ spin chain. So we have a completely isotropic, SU2 symmetric, or partially isotropic, only SZ symmetric, and completely anisotropic versions of these models. From the point of integrability, these bottom 2 are kind of nice and easy, and the top one is rather harder. If you want to turn on kind of deform these nearest neighbor interactions into intermediate or even long-range models, then let's start at the isotropic level. So here there's on the other extreme, there's a spin chain called the Haldane-Shastri spin chain, which was found by Haldane and Shastri independently at the late 80s. And it's also very beautiful. I'll tell you more about this. And in the middle, there's the Inozemtsev spin chain, which some of you might remember a bit from ADS-CFT. Now, as you see, there are some question marks here. So this landscape is not completely understood yet. So there are some models. I mean, we're hoping that there are, in particular, some model here which kind of really, in limits, give rise to all of these spin chains here. And if this would work, and we would really understand such a model, we will really understand a lot about the integrability, even if you only care about the Heisenberg spin chain. I think we will learn a lot about what integrability really means and can look like and so on. So this is kind of the picture that I want to keep in mind. And this is kind of the outline of the talk. So I'll start with Heisenberg XXX, nice and easy. We understand it rather well. And then we'll deform via intermediate range to this long-range Haldane-Shastri spin chain. And I'll show you some of its features. I will be quite qualitative. So the details you can find in our papers, or you can ask me about it later. But I would like to just give you a flavor of what's happening here. And then once we are all the way in the long-range setting on the isotropic level, then I will outline some of the algebraic tools that appear here, and they allow you to Q-deform this, so turn on some sort of partial anisotropy and break part of the isotropy, if you wish, to go to this Q-deformed Haldane-Shastri spin chain. Right, so I'll start with just the isotropic level. So a typical anatomy of these isotropic spin chains are as follows. So you take, let's say, L spin 1/2 sides. We have a Hamiltonian on it, which I will take of a pairwise form. So we have pairs of spins, like here, interacting between I and J. The interactions are basically the standard spin exchange interactions, one sort of the anti-symmetrization of spins. You can write it in Pauli matrices if you want, just at longer ranges than what you're used to for Heisenberg. And then there's some pair potential here, which should be translationally invariant and symmetric. And this controls the interaction strength between sides as they go further apart. So an example of a pair potential that we know very well is the case that forces the distance between two sides to be 1, so that the sides are nearest neighbor. Another example is the Inozemtsev spin chain. It's a little bit more complicated, and it has an elliptic pair potential. So it's up to some normalization factors. It's a Weierstrass P function. If you don't know this, it's fine. It's just a doubly periodic function. So in one limit, it gives a 1/sin squared. So this is a function which, of course, has a real period. This is if you send this imaginary period to 0, to infinity, in fact, I infinity. If instead you send the real periods to infinity, you would get 1/sinh squared, which has an imaginary period, right? So you kind of think of the Weierstrass P function as a generalization that contains both of them, and it's doubly periodic. One of the periods is the length of the chain for periodic boundary conditions, and the other one is it's a parameter which controls the interaction length. So in this limit, if you normalize this correctly, you get this Kronecker delta function for nearest neighbor interactions, and in the other case, you get this 1/sin squared, which, by the way, has a rather nice geometric interpretation. If you think of the chain as sitting in the unit circle in the complex plane, then this 1/sin squared is precisely 1 over the square of the chord distance between the two particles. So just the length, so it's 1/r squared with r the distance between these two sides. So that's rather nice. Now, the Heisenberg model, of course, comes from studying magnetic materials, as I already mentioned. The Inozemtsev model had famously a guest appearance in ADS-CFT by Didina and Matthias, who showed that up to some loop order it appeared in ADS-CFT, and then they went a bit further and it didn't actually really kind of hold, right? So it's but this really sparked interest in the Inozemtsev spin chain, and actually this is really the reason why Rob and I are working on it as well. So I think it has kind of rekindled the interest in these type of models. This Haldane-Shastri spin chain is interesting for various reasons. One is that you can think of it as a lattice version of the fractional quantum Hall effect. So it exhibits, it's a lattice model, but it exhibits some sort of fractional exclusion statistics. So there's some sort of anyons in a certain setting, in a certain sense. And also it has an antiferromagnetic wave function, which looks a lot like a Laughlin type wave function from the fractional quantum Hall effect. So Haldane was interested in this for this reason, that it kind of has, it's a lattice version of something that he liked a lot. Another application is to conformal field theory. So it's actually realized that these models are in the same universality class as Heisenberg and actually Inozemtsev. So they're described by a SU2 level 1 Wezomina-Witten theory. But one thing that's rather interesting about the Haldane-Shastri model is that in some sense it's as close as possible to being an exact truncation of the conformal field theory. So the spectrum here is extremely simple. There are no finite length corrections, if you wish. And there are certain characters that you can compute, and they really give term by term the characters of the affine Lie algebras that occur in the Wessel-Witten theory. So it's really kind of like an exact truncation. The coefficients that you compute for a certain length, they don't change if you increase the length. So it's really very nice from that point of view as well. Now, in terms of quantum integrability, of course, the Heisenberg model is a paradigm for quantum integrable models in general. The Haldane-Shastry model instead is a paradigm for long-range quantum integrable models. It has a very, very special structure, as I kind of already mentioned through these properties here. And I'll show you a little bit more of this. And the integrability here looks rather different. The Inozemtsev spin chain is actually quite interesting because it really challenges our understanding of quantum integrability. So we believe that this is quantum integrable, but it's not really known whether this is the case. And in one way, this can be understood because the way that quantum integrability appears on the left is rather different from the way it appears on the right. So there should be something that really interpolates between the two. And this is a hard problem that we're working on for a long time already, and others too. And there's some progress in this direction, but it's really a long way to go before we really understand this. All right, so let me show you a little bit qualitatively what can happen. So let's take a length 6 spin chain. You just put it in Mathematica. You, let's say, diagonalize per Magnon sector, and you can compute the energies for various values of this interpolation parameter kappa, all the way from Heisenberg through Inozemtsev to Haldane-Shastry. So here we see the energies, and here we see this kappa. And so at the Heisenberg limit, there is some spectrum. It looks whatever it looks like. And then there's something interesting happens. So these energy levels, as we start to increase the interaction distance, these energies, they start to move. Actually, they start to go up, and they can sometimes cross, and they really cross, which is believed to be kind of a hallmark of integrable models. So this already hints at the Inozemtsev model being integrable in a certain sense. Normally, the energy levels would repel because vectors would mix. But if there's enough symmetries, then the vectors are kind of protected and they can't really mix. So that's why these crossings are very interesting. And then as you go all the way to Haldane-Shastry, you see something. Let me just finish this. Something very interesting to happen. So you see that certain levels can get close to each other and in fact merge in the Haldane-Shastry limit. So there are two things that are very special in the Haldane-Shastry limit. One is that these energies that occur, they're very regularly spaced. So you see that this distance here is exactly the same as the one here. It's the same as here. This is twice. This is 3 times that. This is the same. This is 4 times that, and so on. So it's extremely regular, which is related to the fact that in fact there are only statistical interactions, but no really bound state energies, or no only real rapidity. So it's very, very special model. And then there are certain exclusion rules, like Pauli type of rules, which say which momenta you can select. And from that, you can completely write down explicitly what this energy spectrum looks like. So that, again, shows that this is a very special model. Alessandro.
Yeah. So the fact that you have energy levels merging in the Haldane-Shastry limit is, I guess, you will probably explain us the result of some symmetry, I guess.
Yep, that's right.
The crossing, does it appear at random places, like just some particular level crosses some place, or
Yes.
there are like generic places where there is some enhanced symmetry that leads to this crossing of levels, which may be some other degeneracy?
We've looked a bit at this, so I'll tell more about all of this, of course, but let me outline something that's a little bit more detailed than what I will. So what we really did for the two-particle sector is that Rob and I looked at we really solved the beta equations in all the different classes of solutions, and we followed the beta roots as we varied the parameters. And something interesting happens there, but those values at which this of kappa, at which these interesting things happen, they don't seem to be related to these crossing points here. So no, this doesn't seem special in any way, except that they just have to cross somewhere, and it happens. These look like they're maybe at the same point, but this is different, and this is quite different again, and this is... So, no, it seems to, from as far as I know, that doesn't seem to really have any significance. Are there any other questions at this point? No, then I'll continue. So I already mentioned something, but let me just outline. So I would like to make a distinction between different notions that are closely related. So firstly, there's exact solvability. This means that by whatever trick, you can write down exactly the spectrum, at least in principle. So for instance, I would say that the Heisenberg spin chain was known to be exactly solvable from the work of Bethe onwards. However, Bethe's work showed that the Heisenberg spin chain is very special. You have quasi-momenta, and there seem to be quasi-excitations, and all sorts of nice things. Factorized scattering seemed to happen at the level of the coefficients. So this was not really, it's a kind of an observation, but not really understanding why it happens. So I would say that quantum integrability, for me, gives an algebraic understanding of why it was exactly solvable. So it's a deeper and more precise sense in which you're exactly solvable. And here, to be precise, I mean Young-Baxter integrability. So there should be some underlying Young-Baxter equations, kind of like a microscopic definition of integrability. And of course, this came from Fadeev and the others, and Jimbo and Miwa and so on. They did a lot of very nice work on quantum groups and related things to show that you can really understand this exact solution from an extremely nice algebraic point of view. Moreover, this also gives rise to a family of higher Hamiltonians, which is kind of, it's like a nice, if you look at the beta solution, you expect that there should be extra symmetries, and then via the connection to the 6-vertex model, Sutherland showed that indeed there's a generating function for conserved charges, so they're actually higher Hamiltonians, and so it has these higher Hamiltonians, lots of symmetries, which is good. That's kind of the quantum version from what we expect of classical integrability, and so both of these come from quantum integrability. Now, on the Haldane-Shastri side, we have all of these. It's exactly solvable. It was then found to be quantum integrable, and in particular, you can explicitly write down higher Hamiltonians. For Inozemtsev, it is known to be exactly solvable via a combination of the beta ansatz and some sort of things that happen at Haldane-Shastri. And we were able to really follow, as I mentioned before, these exact solutions here, at least for the two-particle sector, all the way from Heisenberg to Haldane-Shastri. At the level of the rapidities, at the level of the wave functions, we get extremely nice matches in the limits. And here there's a proposal for higher Hamiltonians, and there's a proof that the first two non-trivial of them commute, but in general it's not known that all of them commute. So at this point, this is kind of believed to be true, but it's not really settled yet. And in particular, there's no idea of what the quantum integrable structure should be at the moment. So it's kind of interesting. At the moment, I would say that this is really a model that shows that exact solvability need not be quantum integrable. Of course, we hope that, they will all come together. All right, so what I'm going to do now is I'm going to take the two-particle sector for arbitrary length, and I'm going to first start at Heisenberg, then I'm going to show you what happens at some random value of kappa for Inozemtsev, and then I'll show you a bit more about what happens for Haldane-Shastri. So we start with Heisenberg. So here is a plot of the momentum, the total momentum of so this is two particles, so there's a total momentum, which is the sum of the two quasi-momenta of the separate magnons, and this is from 0 to 2 pi. And then here is the energy with some units that I've suppressed. And what you see here is that this spectrum, consists of three types of solutions, if you wish, to the beta equations. So firstly, we have this yellow one, which is just a dispersion. So if you were looked at single magnons, then you get this quadratic, the sine squared, right, as we know very well. And if you apply the lowering operator, you get solutions at m is 2. So that's what this yellow curve here means. Then there are lots of blue dots, and I've indicated kind of open blue dots and solid blue dots. The open blue dots might be slightly hard to see, but the point is that here there are solutions which have real quasi-momenta, and they're very close to their kind of bare values. So these particles interact a little bit, but very mildly. And these open circles are the energies that you would get from just looking at the, if they were free particles, just free particles, then they have their separate contributions. This is their energy. Then if you actually take into account the interactions, the energy moves up a tiny bit, but only very little. Now there's a different type of curve, which is drastically different here, and this is the bound state curve. So there are solutions which have complex quasi-momenta. For two quasi-momenta, the two are just complex conjugates, and in fact, its energy here is given, well, asymptotically, and to very good approximation for finite size, by half the dispersion. So you see that if you have momenta kind of close to pi, let's say, then there's really a gap between the bound states, at least for m is 2, and all these real quasi-momenta type of solutions. In terms of representation theory, we can also understand this picture and actually the general length picture, so it's more or less as follows. So here I draw a picture of the Hilbert space. Each dot represents a basis vector in some, a particular good basis, namely an eigenvector. And I'm ordering them per number of downspins. So this one has 0 downspins, so it's just up, 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 up everywhere. And then there is 1 downspin, these vectors, 2 downspins, and so on, all the way down to all downspins. And of course, by SL2 symmetry, we know that the big Hilbert space should decompose into SL2 irreducibles by Clebsch-Gordon. So if we have 5 sides, then if you do Clebsch-Gordon decomposition, you get 2 to the tensor power 5 is 6 plus 4 times 4, and then plus 5 times 2. So here you see the 6, 4 times 4, and then 5 times 2. Physically, we can understand this a little bit better. This is the ferromagnetic pseudo-vacuum. With all its descendants. These are the magnons, which you get from translational invariance, so they're also very simple. With its descendants, the yellow point, this here corresponds to the curve that we see here. And then there are some really m equals 2 highest weight states. And they come in 2 classes, indeed. There are the scattering states. Here, for this length that I took here, there are only 3 of them. And then there's some bound states, which would lie on this curve here. OK. So this is all standard representation theory, and it's nice. Now let's see what happens if we turn on long-range interactions. So first we go through some point of Inozemtsev, and you see things change, but mildly so. So here the dispersion and this kind of crossing happen to go through the same point. That's no longer true here. It's not so important. You also see that the bound state curve starts moving up a bit. So it's no longer at half the bound state curve. We can, by the way, compute this exactly. It's some elliptic, known elliptic function. And you see, well, if you look very carefully, you see that these 2 points are slightly closer to each other than they were on the Heisenberg side. And if you increase the interaction distance, then these points are getting closer and closer to each other. So the particles become more and more like free particles here. And indeed, this is what happens if we go all the way to Haldane-Shastri. So here we are at Haldane-Shastri. We no longer have open circles. They've really merged in the limit. So it really supports this claim that these particles are basically free particles that only interact through their statistics. There are certain rules that say which momenta you can pick. And besides that, they're just the literal sum of one particle energy. So for instance, if you would take, one magnon here and another magnon here, then there will be really, their geometric sum will be the point exactly there, right? It's really precise additive. And the other thing that we notice is that, okay, so this dispersion became really nice. It's just a quadratic function in the momentum, so that's a very pleasant feature. And moreover, by the way, quadratic together with this exact quantization of momenta means that we get these special values that I showed in the previous plot. They're very easy to get. If you have these kind of things, they will precisely come in 2 pi squared over the length squared, and that was the units for this plot that we had before. So something else that is very interesting happens. This bound state curve in the limit really merged onto the dispersion relation. So what this indeed means, as Alessandro already anticipated, is that there's some hidden symmetry, and it turns out to be a Youngian symmetry. So you remember from the Heisenberg model, you have a Lex matrix, an L operator, and we use it for the algebraic beta ansatz. Here it's different. There's another L operator, and it acts by symmetries. There's no algebraic beta ansatz. If you act by A, B, C, or D, you all get just symmetries. So you can use the B operator to lower. And sometimes the B operator just lowers as it did, as the S minus did here. But sometimes the B operator actually can give a linear combination of what you would get from S minus and something else. And what happens precisely is that these bound states, they join with some of the higher M scattering states with real rapidities, and they become affine descendants. So here we have bigger representations because we have a bigger algebra. So here we have basically the same decomposition in terms of SU2, but as the decomposition in terms of the Youngian of SL2, some of the eigenspaces become bigger, and that's the reason for these extra degeneracies here. And if you do the counting, then actually you can see that it's true that for any M, the number of scattering states, so with real quasi-momenta very close to their bare values, is precisely the same as the number of solutions to this rule that gives the Youngian highest weight states. So what we conjecture is that this will persist to general M. At the moment, we're looking at M is 3 to see that if this persists. It becomes harder and harder, of course, but at least we'd like to support this claim with M is 3. That would be rather non-trivial, but I'm quite convinced that it will work. So the lesson is that here, so it seems to be the case that Heisenberg bound states, at some point for Ino-Zemtsev, they basically unbound and they become descendants instead. They get just real quasi-momenta in the limits of Haldane-Shastri, and they really sit together with some higher, lower M scattering state. So
Can I think of this saying that the binding energy is 0?
That's right. That's right. So what happens is the following. So exactly. So this is really interpreted by Haldane as a free gas of anyons, of specific anyons. And actually, if you do higher rank here, then the rank determines the kind of statistics that you have. So there's a simple exclusion rule. Namely, if you have your momenta equally spaced, you can, for SL2, you cannot pick 2 neighboring momenta. So, if you have bosons, then you would be able to pick the same momenta many times. If you have fermions, you can just not pick the same momenta. In some sense, these are like fat fermions. They also take up the neighboring spaces. So that's the only rule in which they interact. So this is called exclusion statistics. So they have some sort of statistical interactions only, but there's no binding energy. That's exactly right. All right, so we are seeing that this Haldane-Shastri model is really rather special and quite different from the Heisenberg spin chain. And here is a short kind of cartoon of how it really works. So here at the bottom, we have the Haldane-Shastri spin chain. And the algebraic setup is that there is some algebraic structure called the degenerate affine Hecke algebra, which in some, its center in some representation gives rise to the Hamiltonians of the trigonometric spin Calogero-Sutherland Hamiltonian. Before we get there, let's actually do something simpler. This thing has a representation just on polynomials, and this is an old and well-known story. It corresponds physically to the trigonometric quantum Calogero-Sutherland model, and it's known to have lots of commuting Hamiltonians and exact closed-form eigenfunctions that are extremely nice. They're called Jack polynomials. So there's some sort of symmetric polynomials that are very, very well understood from a mathematical point of view. So if we take this simple representation, we get this quite simple model of particles, scalar particles moving around. Now, what we can do is we can give these particles spin, and it turns out that this also has a representation of the same algebra with the family of commuting Hamiltonians and some exact eigenvectors. But moreover, by something called affine Schur-Weyl duality. This is due to Drinfeld in the 80s. Representations of this degenerate affine Hecke algebra also give rise to a representation of the Yangian. So in fact, this trigonometric spin Calogero-Sutherland model also comes with an action of the Yangian. And it turns out, and this is not so hard to see algebraically, that this really commutes with this here. Moreover, the Hamiltonians, they come from the centers of the two, which essentially coincide. So the center of the degenerate affine Hecke algebra and the center of the Yangian both give rise to the commuting Hamiltonians here. And since it's the center of the Yangian, all of the Yangian commutes with it. So A, B, C, D are all symmetries. Center, by the way, is generated by the quantum determinant. So it's a bit different from the usual trace that we take for the XXZ spin chain. Now, this trigonometric spin Calogero-Sutherland model, it has particles moving around with spins, and they interact in pairs, quite like actually what happens for a Haldane-Shastri spin chain, and this, again, is no coincidence. There's a special limit in which is called freezing, in which, well, physically what you do is you send the coupling constant to infinity, or equivalently, you send h bar to 0. So it's some sort of semi-classical limit. The spins stay fully quantum, but what happens is that the potential energy starts to dominate the kinetic energy. So the particles, in a way, start to move slower and slower and slower, and they want to sit at their equilibrium positions. And if you do it carefully, then you should see that they want to sit at their classical equilibrium positions, which are precisely equally spaced. They're no longer moving, but they still have spins that interact with each other long range in pairs. And that's how you get from these Hamiltonians here, the commuting Hamiltonians of the Haldane-Shastri model. Moreover, since I said that the Yangian acts by symmetries, there's no algebraic beta ansatz that we can do. But what you can do instead is, with some work, you can show that the number of the downspins here, so the magnons, are actually governed by a very special version of this scalar Calogero-Sutherland model, which is extremely nice because we know its exact eigenfunctions. They're these Jack polynomials. So Jack polynomials in just the number of downspin many variables with a very special value of the coupling constant precisely give the eigenfunctions of the Haldane-Shastri spin chain. So this is very special. This is a closed form solution. So there are no beta equations to be solved. This is really completely exact and explicit. All right. Well, this was just a cartoon. Of course, there are details. Let me mention again. So there is actually a duality playing here. So you know from representation theory, maybe Schur-Weyl duality, you have the symmetric group acting, and it commutes with GLN or Lie algebra GLN acting. And there's an affine version of this, which relates representations of the degenerate affine Hecke algebra with relations of representations of the Yangian. So that's one example of a duality that shows up in these long-range spin chains. Are there any questions at this point? So this was what I wanted to say about the isotropic models, and now I'm going to kind of take off and go into the Q world, so start to really deform in another way. But I think it's a good moment to see if there are questions.
Maybe seeing as we're at this point now, you said there's you have this algebraic description of the Haldane-Shastri, but there is no known algebraic description of the Zemtsev.
Yeah, that's right.
Are there ideas for whether there would be new mathematical structures that need to be introduced, or?
So it's a work in progress. I cannot say too much about it. There are some ideas for sort of this side of the story. This side of the story, it does not work there. So really, this sort of quantum group kind of action or anything towards an algebraic beta ansatz.
When you say does not work, you can prove that
well, if I do the same that I know how to do for Haldane-Shastri, it does not work for Ino Zemtsev. Okay. So really something completely new will be needed if we want to understand a similar picture for the Ino Zemtsev spin chain. So that's what I mean by kind of quite interesting. If we would manage to do this, it would really completely change, I think, well, both mathematically in terms of representation theory, but also physically in terms of integrability, what it means, what it can look like to be integrable. So it's a very hard problem, of course. Any other questions? Okay, then I'm going to continue. Right, so I think we're halfway the talk more or less, and that makes sense because we're now going up to the second level. I'm not going to talk about the third, so we're halfway. And in fact, a little bit over. So, okay, so this is the same picture as I had before, and the representation theory is very nice. Everything is understood how to Q-deform the previous setting that I showed you. So rather than the degenerate affine Hecke algebra, here we have something called the affine Hecke algebra. It is quantum affine Schur-Weyl dual to quantum affine algebras or quantum loop algebras. It's only level 0 representations, so they're just quantum loop algebras. And if we start again with the affine Hecke algebra, then just like the degenerate affine Hecke algebra gave rise to commuting Hamiltonians and eigenfunctions, joint eigenfunctions of the trigonometric Calogero-Sutherland model with Jack polynomials as wave functions. This affine Hecke algebra by work of Cherednik gives rise to the trigonometric McDonald-Ruijsenaars model. So it's kind of interpreted as some sort of relativistic or difference version of the Calogero model. And it, again, has extremely nice eigenfunctions that are called Macdonald's polynomials. They're a very nice family of symmetric polynomials that are very well understood mathematically. And this, again, comes from the center. Now, you can, once again, introduce spins, and you get a spin version of this trigonometric McDonald-Ruijsenaars model. And then you can repeat the same. Well, this model is special in that we have both commuting Hamiltonians coming from the center here. We have exact eigenvectors sort of coming from the center here. And moreover, we have an action by symmetries of the quantum affine algebra. And it's still true that the Hamiltonians are also generated by the quantum determinant on this side. So the picture is really the Q deformation of the previous picture. And then by freezing, so taking the same limit, this time you get, well, again, a spin chain of equally spaced particles, which now interact in a much more complicated way that I will show in a moment. And this is a Q deformed or partially isotropic or XXZ-like version of the Haldane-Shastri model. Again, its wave functions for M down spins are governed by an M particle version at a very special value of the coupling of this trigonometric scalar Macdonald model. So we have very nice eigenfunctions explicitly in terms of Macdonald's polynomials. Moreover, I mentioned that here for Haldane-Shastri, the only interactions were through the statistics, and there was a very simple rule. You could not pick two neighboring quasi-momenta. This rule does not change. So this is still completely statistically interacting otherwise free particles. So it's very, very simple. It still has fractional statistics in the exclusion sense, and so on. Right, so now, before we go here, I want to use another duality and go to a sense. So this affine Hecke algebra that I have here, it has a duality. This was found by, well, really it's a double affine Hecke algebra that has a duality by Cherednik. And so rather than picking the representation that is relevant here or really here, you can take some sort of dual representation in a precise sense. And this gives rise to, so we have again the affine Hecke algebra, and it gives rise to the inhomogeneous six-vertex model. So what I mean is that the representation that you get here can be understood as being related to the inhomogeneous six-vertex model. By quantum affine Schur-Weyl duality, it comes again with the action of the quantum loop algebra with an L operator that is dual in the sense of Cherednik to the L operator that we had for the spin McDonald-Ruijsenaars model. And here, there's something that's a little bit similar to what happened for Haldane-Shastri. So we can take some logarithmic derivative, as we know very well, to get something that I would want to call the inhomogeneous Heisenberg spin chain. You might not have really thought about this, but I'll show you more about this in the next slide. And then we can take a special limit, the homogeneous limit, in which all these inhomogeneities become the same. And then we get our good old Heisenberg XXZ spin chain. So the picture here is a little bit similar. An important difference is that here, rather than taking the center of the quantum affine algebra, as you know very well, we use, to get the Hamiltonians here, what we get here is the transfer matrix, which corresponds to an abelian subalgebra called the beta algebra. So it's something else than the center. It's larger, so it commutes with less. And here we can take logarithmic derivatives, and then we get all these commuting Hamiltonians of the inhomogeneous and in the limit homogeneous Heisenberg XXZ spin chain. So the picture is somehow, in a precise sense, at least at the top, is dual to the picture that we had for Haldane-Shastri. So I think this is rather interesting, and more there is to be understood. In particular, coming back to Inno-Zemtsev, it would be really kind of wild to have some sort of something that interpolates between these two dual sides. It sounds like it might be rather difficult, but it would be really cool if it works. All right, so I showed this, what I call the inhomogeneous Heisenberg spin chain. We think of it as a Heisenberg spin chain where the particles are not equally spaced. So let me show you more about this. You kind of, in a way, you already know it, but you might never have really thought about it. So let me first motivate this. So normally we think of inhomogeneities as a computational tool. For instance, if you want to prove the completeness of the solutions to the Bethe equations, then it's much easier if you introduce small inhomogeneities. You kind of break most of the symmetry, so you can easily count solutions. And so you can show that the Bethe ansatz is complete by introducing small but finite inhomogeneities. Also, the proof of the Razumov-Stroganov conjecture used inhomogeneous six-vertex model and inhomogeneous XXZ spin chain to really show this. So this was a very nice observation first for a relation between spin chains and some loop model eigenvectors. These inhomogeneous spin chains also occur quite naturally in, for instance, in n equals 2 supersymmetric gauge theory, you have this beta gauge correspondence by Nekrasov and Shatashvili. So there, you naturally get beta equations which have inhomogeneities. And the reason for this is that in terms of geometric representation theory, which is the mathematical version of the beta gauge correspondence, if you wish, these inhomogeneities are interpreted as equivariance parameters in equivariant K theory. So mathematically, they're extremely nice as well. Now, more physically, inhomogeneous spin chains are interesting for CFT. So if you take unimodular Q and the scaling limit, where Gleb Kotousov can tell you much more about this, then you get interesting, by introducing inhomogeneities, you get a more rich landscape of CFTs there. And moreover, of course, these inhomogeneous XXZ spin chains are interesting for other limits. For instance, quantum but non-affine Godin models occur as a special limit of these inhomogeneous XXZ spin chains, and various other things also occur as special limits. For instance, you can take the staggered 6-vertex model and the staggered XXZ spin chain, where you take two different, like periodically two different inhomogeneities, and then you get slightly longer range interactions. Okay, so this is a motivation for this inhomogeneous Heisenberg spin chain. By the way, remember that I'm really talking only about finite length here. So what we do is the usual thing. So we take an R matrix, the 6-vertex or XXZ R matrix, which obeys all our favorite identities, the Young-Baxter, unitarity, and initial conditions. And then we make the transfer matrix, which is graphically, so here I have a product of R matrices, and then I take the trace over it, which I indicate by these little arcs. So graphically, this is the transfer matrix, and here you see it in terms of a trace over the auxiliary space of R matrices. Now, of course, we know that because of the Young-Baxter equation and generic invertibility, this thing here of the R matrix, this thing here obeys, forms a commutative family of operators, so it's a good generating function for Hamiltonians, and that's what we do to get the inhomogeneous Heisenberg spin chain. So in analogy with the homogeneous case, I define the inhomogeneous Heisenberg spin chain Hamiltonian as the logarithmic derivative of the transfer matrix, but we have to do it at a particular point. And in this case, the good points are precisely the inhomogeneities, because that's where some of these things simplify. If I pick any one of these, if I pick this U to be any one of these inhomogeneities, then we can use this relation here that says that if two lines meet with the same spectral parameter, then you just get the permutation. So the thing kind of breaks open. So these are the good points to do it. So we get L different Hamiltonians, Hj. So let me kind of talk you briefly through the graphical computation of this. I think it's rather nice. Of course, it also works in a homogeneous spin chain, so you can nicely compute it graphically. So first, let's think about this derivative. So this transfer matrix is a product of stuff. So its derivative is a sum of things where we take the derivative of any single of the factors. So that's what I do here. So I indicate this derivative by a big dot on the R matrix. And then this derivative can either be to the left of the point where we, which of the inhomogeneity that we took. It can occur at the same point, or it can occur to the right of the point where we broke it open. So of course we set this U to be Zj. So indeed these R matrices here, they open up just as governed by this rule, by the initial condition for the R matrix. Now there's a little bit of trickery. Of course, here we can see some simplification. So this here is precisely a copy of this unitarity picture. So we can pull this line all the way to just to the right of the Zi, and the same here. So we can pull it all the way to just to the right of the Zi. Here we cannot really simplify it so much. Now in the computation, the next step, which is a little bit non-trivial, is to notice that basically, well, I guess I should really draw this. So we have now reduced our computation to mostly these type of pictures. We have an R matrix here, and then the derivative of the R matrix here. And what you can show is that this picture here simplifies to something nice. Namely, it basically becomes what I here denote by this wiggly line. So if you take the up to a factor, the derivative of the R check matrix, which we know is the local Hamiltonian in the homogeneous case, then I'll indicate it like this, and this picture that I showed on the blackboard there becomes some function, which I denote by this potential. It's quite simple. I'll get back to it in a moment, times this usual derivative, this usual local interaction. So graphically what happens is that now, up to some factor, we have this zigzaggy line. So what happens is that this particle at site j always goes to any point to the left of it and then interacts via the usual nearest neighbor interaction. And this transport happens via R matrices, because all these crossings here are R matrices. Then if we have this, basically the same happens. The particle at site j always wants to go to the left, and if necessarily, periodically to interact with the particle that we took the derivative at. And then there's something kind of funky. What happens here is that the particle at side J goes to the left. Then it comes back to its own side. It kind of interacts with itself in the future. It goes back to the right to interact with itself from the past, and then it continues. So you can make a sense of this algebraically. It's kind of simple. What you do is just you write the R matrix of a product with some coefficients of a unit, like any one of the basis matrix in the left tensor factor and then any one of the basis matrix in the right tensor factors. And then you just have lots of R matrices in between. So you can really write down formulas. I can put this in Mathematica, and it's completely happy to check that these things commute for different J, for instance. So these interactions are rather non-trivial. Let's just understand them a little bit better. Let's send all these inhomogeneities to 1. Then what happens is that I can basically use this picture everywhere where I don't have, well, this picture from the derivative. So all these things open up, and what happens is that you just get nearest neighbor interactions always. And that gives back the usual nearest neighbor Heisenberg spin chain. All right? So if you don't like the inhomogeneities, you can do the same graphical computation to get the usual Heisenberg Hamiltonian, but it's actually not too much harder to do the inhomogeneous case. Now this function here, if you would write this in additive notation rather than multiplicative, it looks just like a Q deformation of the 1 over sine squared that we had before. This is quite easy to see. So it's kind of like a point splitting of the 1 over sine squared. So it's actually not a kind of a very strange function to appear. And I've just normalized this here by something so that I can take both the homogeneous limit and I can send Q to 1 and there are no singularities. So this here is the inhomogeneous XXZ spin chain. Of course, we kind of secretly all know this because let me just repeat it. So this is the same Hamiltonian that I just computed for you. Of course, we know that its exact spectrum just comes from the algebraic beta ansatz with inhomogeneities up to solving beta ansatz equations with inhomogeneities. But this is a standard computation that we've all done. So here I show you the Hamiltonian of the thing that we've been diagonalizing in those exercises where we included inhomogeneities. Now, we get back to the Q-deformed Haldane-Shastri, which is related to this Daha duality of Cherednik. And I'm just giving you what the result looks like. So it looks a little bit complicated, but actually it's simpler than this inhomogeneous Heisenberg spin chain. So the Q Haldane-Shastri Hamiltonian is the sum over pairs of sides. And this, we only have this interaction where the spin goes from the right to the left, just like it did in the first part of the sum here. To interact with Zj here, and then it moves back. And here, all the transport is by R matrices, and this local interaction is just the usual exchange interaction. So here we only have the simple part, really, of this thing here. There's no of this periodicity happening and none of this weird stuff happening. And then there is, again, this potential, which here, actually, I don't need to normalize because by freezing, which I mentioned, these values of z's, the coordinates of the particles or the inhomogeneities, they have to be fixed to the jth power of the primitive lth root of unity. So again, these are the positions of the particles sitting on the unit circle in the complex plane. Then the jth particle is just the jth root of unity, so equally spaced and nicely. So you take this somewhat involved expression and you evaluate it, that's how we call this, the inhomogeneities to these specific roots of unity, and that is the Hamiltonian of the Q-deformed Haldane-Shastri model. So it looks complicated, but it's less complicated than the one that you've secretly already known all your life. And moreover, if you take Q to 1, then this function here just becomes the 1 over sine squared. And this thing here just becomes the anti-symmetrization. So this is just a Q deformation of the Haldane-Shastri model. Moreover, this deformation here is precisely so that all the nice properties generalize, as I outlined. So in particular, it has quantum loop symmetries, so lots and lots of symmetries, big eigenspaces. And we can understand its exact spectrum via some connection, as I already outlined, to the Ruijsenaars-McDonald model. And we have exact wave functions, which are in terms of these McDonald's polynomials in closed form, no beta equations to solve. So in some sense, the spectrum, the models may be more complicated than normal XXZ, but the solution is much easier. So it's very delicate so that everything works extremely nicely. And of course, it's a long-range model. And moreover, it's actually a multi-spin model. So if you think of this as the R matrix, then what can happen is that if you have a downspin here, the downspin can either go to the left or it can kind of drop off this line. So really, multiple spins can interact at the same time. So the interactions are rather complicated. And I understand from Didina that she thinks that the ADS-CFT Hamiltonian might well be long-range and multi-spin interaction. So when she saw this formula the first time, she was very enthusiastic because it was getting towards what she was hoping would be relevant for ADS-CFT integrability. Now let me just advertise something that we've been doing recently with our master student, Ayman Tufik. So of course here, compared to normal Haldane-Shastri, we have this parameter Q, the deformation, and you can play with this, and in particular, you can take some nice special points. So one thing that you can do is you can set Q equal to I. the simplest root of unity, non-trivial root of unity. And for Heisenberg, it's well known that this is related to free fermions. You can do a Jordan-Wigner transformation, very simple. In momentum space, the Hamiltonian becomes diagonal, and you can just read off the spectrum. So here, everything is much more complicated because these interactions are more complicated. But we can prove that, in fact, it is a free fermion model in the sense that there are fermionic operators, F and F dagger, so that this thing is really, in the end, quadratic in F and F dagger. So it's just a model of hopping, long-range, complicated way hopping, free fermions at Q is I. Moreover, if we take odd length and we make sure that the Hamiltonian is kind of regularized in this limit Q going to I, then we have, it's quite interesting, a massless relativistic dispersion relation. So it's really just has two branches away from the origin, just like a standard relativistic dispersion for a massless particle. And for even length instead, all the eigenvalues become 0, but we get Jordan blocks, and we get rather big Jordan blocks. So this is quite interesting. This is, for the Heisenberg spin chain, there's a special version which is UQ SL2 invariant, and that 2 is known, if you take Q to I, to have Jordan block structures, but in that case, the biggest Jordan blocks are always just 2 by 2. We get arbitrarily large Jordan blocks, and I think it has to do with the fact that we have much more symmetries, and these Jordan blocks are somehow related to the affine descendant structure. But this is something we don't really understand yet, and we're working on. Moreover, we're trying to get an...
Sorry, in this given L, you're recovering this Q-deform structure at roots of unity?
I mean...
Q-deform text executor is worked by Deformation, I think Grenadino who started exactly...
No, so it's different, as I mentioned. So what they often... No, right, so if you do normal Heisenberg xxz at Q is I, you can either do the periodic one, which is you do Jordan-Wigner, or you can take one of these UQ-SL2 invariants, for instance, the open one, or this sort of Bray-translate quasi-periodic one, which they like a lot because it's related to temporally Lieb and quantum SL2 and all these kind of things. Now, if for the latter you specialize, then, as I mentioned, you get Jordan blocks, but it's much smaller. So in terms of representation theory, here we seem to have a different type of free fermion model, which has kind of a richer representation theory. Which maybe is not so strange because we started with a model with richer representation theory. So, but it's very nice to see it actually work in practice at this special point. Of course, this model, so we're hoping to find an explicit expression just in terms of the fermionic operators of this Hamiltonian. For even length, it's not too hard probably, and I'm sure that we will be able to get such a formula. For odd length, more terms survive the limit and it's harder, but maybe we would be able to get it. And I think this would be rather nice because this could be an interesting model for condensed matter physics. Okay, so this is really already the outlook of my talk, so I guess I'm a bit ahead of time. But so let me just get back to this landscape. I've shown you from the Heisenberg xxx, which we know very well, how to go by turning on intermediate range interactions and then long range interactions, what happens to the spectrum via this beta ansatz exact solution through Inazemtsev all the way to Haldane-Shastry. In terms of representation theory, we understand Heisenberg very well, and we understand Haldane-Shastry in some sense even better. It's even nicer. There are no beta equations and so on. In Inazemtsev, we don't know the algebraic structure, but it is exactly solvable, and by looking at the spectrum, we expect it to be integrable. And then once we understand the algebraic structure of Haldane-Shastry, we are able to Q-deform it to get a partially isotropic version of it. And I showed you that actually, even though the Hamiltonian looks a bit complicated, it's very closely related to something which is not quite a Heisenberg xxz, but the inhomogeneous version thereof. And in some sense, those two models, or really their kind of parent models, the spin Ruijsenaar-McDonald here and the inhomogeneous six-vertex model here, are dual in the precise sense of representation theory. So I think this is a very appealing picture. And of course, it would be fantastic to try to fill in some of the blanks in this landscape. This one here is the first one to be filled in. There's some related work which gives a spin chain which is an elliptic spin chain. So it looks like it deforms Haldane-Shastry, but it does not deform Inazemtsev, and so it doesn't really fit in this landscape here. And then, of course, if we go to the fully elliptic in terms of quantum groups level, this is going to be a very tough problem. But if we can understand something there, it would be amazing. And I think we will learn a lot about integrability in general. And just, so what I really advertise is this underlying picture of, well, so first I should say, of course, what we want to do is, now that we're kind of here, we want to conquer the rest of the world and understand everything, including all the Heisenberg limits. And I think we will learn new things about Heisenberg in this way. And the underlying picture that we always have in mind is this picture of quantum many-body systems without or with spins. And this is precisely what happens for Haldane-Shastry, which is related to trigonometric Calogero-Sutherland. It's Q-deformation, which is related to this Ruijsenaars-McDonald. And then, hopefully, Inazemtsev is somehow related to an elliptic version of Calogero and Ruijsenaars. And this limit is extremely hard to take from the elliptic model, but it should be something like a Lieb-Lininger model, which has some sort of contact interactions as well, but in a continuous sense, so it's much less regular, and we can't really take this limit. But I hope that we can actually understand the Heisenberg spin chain in some sense by freezing these type of models really understood as properly as the limits from these elliptic models. So I think this would be a really new and nice point of view, even for the integrability of the good old Heisenberg spin chains. So yeah, that's all I wanted to say.
Thank you very much for a nice talk. Questions? So maybe I can start. I have a couple of questions. First, can you just go back one slide? Do you have reason? Are there sort of concrete reasons to believe that this world that you want to conquer exists?
Optimism, for sure. I think. So I think that the fact that, so nowadays, I didn't really mention this, but nowadays people in quantum many-body systems are working on this thing which is called the double elliptic system, which is kind of elliptic both in the coordinates, like all of these, and in the momenta. And this is very hard, but people are currently working on it. And so I'm sort of hopeful that one could freeze this in some sense, and if one can, then it should correspond to this model at the top. So various bits and pieces are already in place.
So there are kind of, the other question I had was, you had this, let's see if I can remember. So you had this relationship between Heisenberg XXZ and Q-deformed Haldane-Shastri.
In terms of the Hamiltonians or this previous?
This story. So you first did this duality and then...
Right.
How does this sit inside your picture of 9 models and...
yeah, that's a good question that I don't
it.
really know the answer to. So this Cherednik duality seems to, in a slightly suitably modified sense, kind of in some sense reflect the picture through its middle, but I don't know what it does except at the strict boundaries.
Does it work in the at the bottom, at the rational level?
Yes, it does, but the rational level in terms of, so the affine Hecke algebra is much nicer than this degenerate affine Hecke algebra. So here you take some sort of limit which breaks a little bit the symmetry of the Cherednik duality. But in principle, it should also work here. Yes, but it's actually mathematically the Q deformed level is actually nicer than the isotropic level. But yes, it should work. I kind of have to work out the details, but I'm convinced that it will work.
Maybe can you just...
Do you think there exists this affine duality for elliptic Daha or not?
Well, do you think elliptic Daha exists in the appropriate sense?
There are a few people that are proposing it.
Right, so there is Eric Rains and company. So they have a construction of what they think of as an elliptic Daha, but it's some sort of construction in terms of sheaves and blah, which I don't really understand. In particular, there does not seem to be a presentation in terms of generators and relations. And I only understand this duality at the level of certain, an explicit map on the generators. So yeah, no, I've asked Rains, and he's not able at the elliptic level to give such a presentation, which would be the concrete tools that we need to really do any computations. So unless I would learn a lot of geometry, I'm certainly not able to do this.
Because there is also this, Bernstein-Plücker formulation, which also allows, but there is no algebraic formalism.
Right. That's true.
So, is there any example of a long range or intermediate range for other algebras? Like if you would include not only identity and permutation, but decay as well, like the trace operator, or?
Right. So. Indeed. So for the, let me go back to my favorite picture. Here it is. Yeah. So on this side, we have lots of things that we can do to these spin chains, right? We can go higher spin, we can go higher rank, we can make open boundaries, we can do a twist. There are lots of things that we can do. So here, so let me talk about this limit, because if I don't understand this limit, then I'm never going to understand the middle. So at this level, the mathematics was really kind of rigid and very powerful, but so it doesn't allow everything that we were able to do here. So what you can do for Haldane-Shastri is you can't go higher spin. What you can instead do is higher rank. This connection with the affine Hecke algebra seems to need kind of always, if you have a k-dimensional space for your spins, then you have to have an action of GLK to make this connection via Schur-Weyl duality. And so that's one restriction, but you can do arbitrary SLK. So that's already kind of good. So in some sense, higher rank models exist. And as I mentioned, this is related to different types of exclusion statistics. So you kind of, this K in some sense is a parameter that scrolls through different types of anyons, if you wish. Now, twists do not seem to be possible in this world. But open boundaries are possible. So for Haldane-Shastri, this is known. For Q Haldane-Shastri, I'm planning to work on it, and I have a student, a PhD student who will start next year, and we'll look at this. So I think that absolutely it should work, and it should relate to Kornwinner theory. So there are McDonald polynomials have some sort of type BC analog, which are known as Kornwinner polynomials. And again, I'm quite confident all the structure exists, all the algebraic machinery is present. So it's just a matter of working out the details, and I'm quite convinced that we can do arbitrary 4-parameter K matrix type of things there.
Sorry, just another precision. I'm wondering, when you mentioned this double elliptic
Right, so let me go
structures,
there.
yeah. I don't know. Do you know if there is because people like have this double elliptic Mann triples, and they can show that there is this correspondence to the spin arrest models. Do you know any relations to your framework? If I'm not asking about probably spin elliptic arrest, but at least trigonometric, which would be probably more relevant.
Right. So no, I do not know about this. Do you know, are they quantum or classical spin Reisners?
I think they also have
They're quantum.
quantized.
Okay, so I'm not aware of this work. I don't know about this work, and I cannot comment on this, unfortunately. It sounds
Because
interesting.
I think that if somebody understands this double elliptic reduced to the at least trigonometric spin rest, then there would be many answers to the uplift.
Yeah, absolutely. This sounds like a very fruitful direction. Thank you.
So are there any further questions? If not, let's thank Jules again for a very nice talk. And we'll come back in just a few minutes for the next talk. But yeah. We are at the last talk of the week, and this is a great pleasure to introduce George Linodopoulos, who will tell us about string integrability in brain-deformed holography. Please.
Yeah, you can hear me, yes. So, great many thanks to the organizers for organizing this wonderful meeting and conference, and also for having me here. It's a pleasure to be in Berlin and be able to present my work with, Kostya last February. Started off with Kostya Zarembo last February and continued also, this one, and this is this February. Extended the results of our first papers. And my talk title was suitably adapted to the keywords of this conference. Contains the words integrability and deformations, and this is probably also contains the word dualities, holographic dualities. So here's the plan of my talk. I'm going to start off with an introduction, and then I'm going to pretty much repeat what is known about string integrability within ADS-CFT. And finally, I will describe or say closed string integrability in ADS-CFT, or periodic, closed string integrability in ADS-CFT. And I will, in the final section, I will describe open string integrability, or what is known as also brain integrability in ADS-CFT, deep brain integrability in ADS-CFT. And let me first describe what's the setup of this, that this work belongs to. And the setup is boundaries and defects, the physics of boundaries and defects, which is, of course, so broad. Boundaries and defects are part of real world, Realphysik, say in German. And, of course, it's based on the fact that the real world is really imperfect, has imperfections, and many different point of views, many different impurities, domain worlds, and this is what we live in. And of course, boundaries are really physics. But of course, what I'm going to be focusing on is some formal aspects of defects. And these are, of course, arise, as we all know, or probably most know very well, within holography and the ADS-CFT correspondence, where, of course, we have a boundary theory, which determines and is determined by a bulk theory. Of course, string theory contains open strings, which were, of course, have their endpoints. Can be closed, of course, but the open strings have their endpoints on deep brains, which are themselves dynamical objects and give rise to a great many interesting field of deep brains within string theory. And of course, quantum entanglement, maybe we have a system that is separated in two or more subsystems, and there is a surface or a defect that separates these systems. And what we are interested in is find how the degrees of freedom actually are reduced and give rise to entropies, etc. And of course, there are then applied aspects, and probably the ones that are relevant to the present work is the physics of statistical systems near surfaces, which is completely different, of course, than statistical systems near, not near surfaces in the bulk. Critical exponents are completely different near surfaces. And also topological materials. These materials are known to have some topologically protected modes on their boundaries, on their surfaces. And topological insulator, of course, are prime examples of topological materials. And then also out of equilibrium systems and quantum quenches have been shown to also be relevant to boundaries and defects in the so-called scattering picture, etc. And then, of course, natural boundaries and defects permeate all branches of physics. And this is the general setup. But now I will be focusing more and more to my to the field that I will be exploring. And this has to do with boundaries and defects within quantum field theories and very special types of quantum field theories, which are conformal field theories. And this field is probably owes its beginnings to Cardy, who in 1984 studied, motivated of course by the physics of statistical systems near boundaries, studied the codimension one boundaries within a defect conformal field theory. A conformal field theory in D dimensions. And in fact, it's very clear that this boundary, say at point z equal to 0, breaks translation invariance, and then this gives rise, beginning with a Euclidean conformal group, the system with a boundary respects a subset of this Euclidean conformal group, namely conformal group in one dimension less. And of course, as I anticipated, the presence of boundaries completely alters all that we know about and we loved about CFT correlators. We have a completely new set of conformal data in this case. And of course, the study of higher codimensional defects and the use of them to bootstrap both the original and boundary CFT are part of the conformal bootstrap program. And certain types of defects can really be roughly described by that type of action, which contains, of course, the d-dimensional action, and if it's a con-dimensional one defect, it also has degrees of freedom on the boundary, which interact and interact with bulk theory. And this is precisely the type of defects that we are going to see, but of course in a holographic setup. And I'm interested in defect CFTs that are holographic. That is, they have a dual, which is a gravitational dual, or a string theory dual. And the prime examples, of course, are the of holographic dualities, which I'm going to be deforming by means of D-branes on the string theory side and codimension one walls on the dual theory side. Is the ADS-CFT correspondence, which is of course known to be quantum integrable in the planar limit. And secondly, also the ABJM duality in the version that involves string theory on ADS4 cross CP3, which is again quantum integrable in the planar limit. And yes, these two theories are my prime focus, and I'm going to be examining the string theory side, where I will be inserting probe D-branes and studying the integrability of strings that end on these D-branes, and eventually showing that the boundary conditions for these strings are integrable. And so let me first go through very quickly these theories. Of course, we have n equals 4 super Young-Mills. This is a conformal field theory having exact superconformal symmetry. And of course, as I said, this is quantum integrable in the planar limit, and this integrability was first manifested in the spectrum of scaling dimension by the work of these people, Minahan and Zarembo, Beiser, Christensen, and Staudacher. And of course, integrability solves the spectral problem of n equals 4 super Young-Mills. And of course, we extrapolate to the whole theory and say that this integrability should be present in all the theory, or not only the spectrum, but and the computation of the theory's observables in the planar limit is currently underway. And of course, this also allows us to check the validity of this correspondence in the planar limit. And the same, what was that? I forgot to say, maybe relevant to this work, half BPS boundary conditions in this theory was studied by Gaiotto and Witten. And so now the same is true for ABJM theory, which is again a gauge theory with conformal symmetry and much more maybe potential rich potential structure with sextic and mixed quartic interactions. And again, this was shown to be integrable with regard to its spectrum by Minahan and Zarembo again. And again, there is a solution of the spectral problem of this theory by quantum spectral curve. So much for the gauge theory side of these theories. And now I'll be going to the string theory side, which has also been shown to be integrable in the planar limit and also in the tree level or infinite coupling, classically integrable, that is. And I'll go through the procedure because it's going to be the basis for what I'm going to be doing with open strings. So first one has to define what is strings in this background, and these backgrounds actually, ADS5 and ADS4. And this crucially depends on the fact that these backgrounds, both of these backgrounds can be written as products of cosets, which themselves then, I mean, this product is itself the bosonic sector of a higher supercoset. And this was done famously in this work, which built, of course, on earlier work on writing Green-Schwarz sigma models as cosets on flat space, and this famously showing that this reproduces the Green-Schwarz action. And the same is true, of course, for ADS4 cross CP3, can be written as a coset, which is itself a bosonic sector of a supercoset. And these supercosets are known to be semi-symmetric spaces, what we call semi-symmetric spaces. And these semi-symmetric spaces have been known to be integrable. Sigma models that describe Green-Schwarz superstrings. And this is the Green-Schwarz model that we will be studying. I mean, people who worked on integrability of classical strings in ADS-CFT related backgrounds. And of course, these are, let me explain, maybe, of course, many people have really created all this work. And of course, I just mean to remind certain people who are not really working on this area. And so these are the so-called currents, which are defined in terms of supercoset elements, G. And of course, the fact that these backgrounds are really semi-symmetric means that they afford a Z4 decomposition. So this part is of course this part of, so the semi-symmetric cosets are spaces which have a subset which can be invariant under a discrete Z4 automorphism, omega. And this omega really pertains to this zero bosonic part of the subset of the supergroup. And of course, this is what it, this automorphism is the one that endows the supercoset with a Z4 structure. So semi-symmetric space, symmetric spaces, on the other hand, are just bosonic spaces that afford the Z2 decomposition. But now, once we have the fermions, we have two more, components in this decomposition, which, of course, are carried out by means of a discrete automorphism omega, and I provide the details of this automorphism in here. And of course, we also have a parameter matching between the two sides of this duality, which allows us to write the corresponding tensions in terms of the 't Hooft coupling constant. And so what did I say? Yeah. So these currents, of course, let me go to some formal facts, as I say. So this current, of course, has a vanished curvature. It's very easy to differentiate this relationship and see that it satisfies this equation. And then by using the equations of motion that arise from this sigma model, one can show that there is a flat Lux connection, which is given by this formula here. And flatness means that it satisfies this equation. Again, a flatness condition. And X is the so-called spectral parameter. Now there exists a more convenient form of the current, which is so-called the fixed frame current. The one that we just show here is the so-called moving frame current, big J. Small j is all left current, which is given in terms of this transformation. And of course, this again is still flat, but it gives rise to a more convenient form of the Lux connection, which does not contain the invariant subset, the invariant, yes, so bosonic element. And this is what was famously used by Benham, Polchinski, and Royban to prove integrability of these strings. And let me go through the argument very quickly. So the argument of proving integrability, of course, we know the classical Liouville integrability. We need the number of conservation laws or charges, which is equal to the number of degrees of freedom of a theory. And then these conservation laws can be inverted and typically provide a solution to the equations of motion of classical theory. But now, of course, we have the field theory here that is infinite degrees of freedom, and so we need an infinite hierarchy of conservation laws, which ideally they can be inverted and give solutions. So this is exactly what is meant by integrability and solvability. And in order to actually construct these conservation laws, we need this object here, which is known as the monodromy matrix, which is just the holonomy of this Lux, this component of the Lux connection, of this fixed frame Lux connection. And it's very easy to see how this leads to an infinite set of conservation laws. We just need to differentiate this monodromy matrix. And then by using also the flatness of the Lux connection, which is very crucial, of course, and equivalent to integrability, we arrive at this formula. And then, of course, we have to use take the trace of this quantity and use the fact that we impose periodicity, the strings, that is closed strings. And one can find probably the first charge in this conserved hierarchy. And of course, higher charges, as it was also stressed in previous talks, can be generated by taking powers, appropriate powers of this quantity, this transfer matrix now, because it's just the super trace of the monodromy. And the charges, of course, can be obtained typically by expanding this monodromy matrix around appropriate values of the spectral parameter, and one identifies each of these expansions. So in the bosonic case, so let's take the fermion part to 0, so we are only left with J2 currents. We can identify this with charges, and one can really read off the charges from this relation and appropriately show that these charges are conserved. And this is, of course, the weak sense of integrability. Probably one needs to also have independence of these charges. We cannot really generate infinite charges, and they cannot be really the same charge. They have to be different, and so they have to Poisson commute. And there is very nice work actually showing this independence of the charges. And so much for string integrability. Now let me go to brane integrability. And but first, let me summarize a bit. And of course, I have to define the branes, and I have to define everything. But so holographic defect conformal field theories were first realized in the context of the ADS-CFT correspondence by Karts and Randall in 2001, with a completely different motivation. In fact, they brane deformed holographies, and these holographic CFTs were actually deformations of the dualities, the ADS-CFT duality, ADS-5 duality that I showed you before by brane. And this was done by Karts and Randall in 2001. And of course, I already discussed the boundary conformal bootstrap program. Another technique which can be applied to the study of holographic defect CFTs is integrability, of course, which was introduced to these setups by Deleu, Christensen, and Zarembo in 2015. And this led to a systematic calculation of the defect data. And moreover, recently, well, in 2020, localization methods were also put forward in these setups, and they permit to carry out precision tests of the dualities that I'm going to be showing you in the next slides beyond perturbation theory. So let me go first through the Kac-Randall system, which will define the boundary conditions for our strings. And then I will, of course, try to show the integrability of strings. And first, remind you that ADS type 2B string theory that shows up in the right-hand side of the, as I showed it, and of ADS-CFT duality, is encountered very close to a system of n-coincident D3 branes. And these D3 branes are, of course, heavy objects which curve the space-time around them, and they give rise to a singular space-time. And ADS5 cross S5 and 2B string theory are encountered very close to the throat of this geometry. And the D branes extend along these three directions. And now what Kac-Randall did, they inserted the D5 brane at the point x3, x7, 8, 9, 0. That is, these are 0 and this is 0. Of course, this is the flat configuration, but maybe it's very, very illustrative of what I want to say. And in fact, one can show that the geometry of this probe brane, it's just a single D brane intersecting the D3 branes, or equivalently, yes, I will say that probably in the following, a D5 brane inside ADS5 cross S5. And one can show very easily that this brane will have a geometry of ADS4 cross S2. So this is the setup, the holographic setup that we get. On the bulk theory side, we had 2B string theory in ADS5 cross S5. But now we have a probe D5 brane of ADS4 cross S2 geometry, which bisects this, the bulk. And this, of course, corresponds to a dual CFT, a defect CFT, which was initially, of course, this part was dual to n equals 4 Spring-Mills with SUN gauge group, and this part the same. But now we have also this, the projection of this D5 brane to a wall, 2 plus codimensional 1 wall in 4 dimensions. And yes, and De Wulfe, Friedman, and Oguri studied this. So of course, I showed you the Lagrangian of n equals 4 Super-Yang-Mills, but now this immediately implies that there is another conformal field theory on the superconformal field theory on the defect that interacts with n equals 4 at 0. Yes, and this was studied by De Wulfe, Friedman, and Oguri, and also led to study of spin chains, etc., in the defect setup by De Wulfe and collaborators. And because of the defect, of course, the symmetry of the system is lowered. From bosonic symmetry is lowered to SO32. Of course, this means that we break the conformal translations, and the superalgebra of course is halved, is OSP44. So it's a half BBS defect in this case. But one can also consider adding K units of magnetic flux through the two-sphere of the brane. Remember, the brane had the geometry of ADS4 cross S2, and we can introduce K units of flux. And this means, of course, by energy conservation, that exactly K of the D3 branes will end on the D5 brane. But one can show by going, of course, to the DBI analysis, etc., that the geometry will still be ADS4 cross S2, and it will be stable. So even if K is 0 or K is non-zero, this geometry of the brane is stable against perturbations. And moreover, the embedding of the D5 brane will be described by these equations here, where this is actually fluxed in the units of inverse square root of lambda. And of course, the metric of ADS5 is written here for completeness. And the two-sphere, of course, is parameterized by these coordinates. Yes, and of course, as I said, we now have a tilted D5 branes, where in the case A, alpha different than 0, the brane is tilted now. And on the S5 part, we have a D5 brane, which is a stable two-sphere. This sphere is usually sometimes it can be unstable towards flipping off the sides of the sphere, but this has been proven to be very stable in the presence or in the absence of flux. And now the setup, the holographic setups in the presence of flux is this one. As I said, because of energy conservation, K of the D3 branes have to end on the D5 brane. And this, of course, induces a decrease in the gauge group rank on the left-hand side. But still on the right-hand side, we have the same setup. And this has been shown again by Katz and Randall to be equivalent to the development of a non-zero vacuum expectation values for the fields of n equals 4 super Young-Mills. And one can use this fact in order to compute correlation functions as Higgs condensates of gauge invariant operators of n equals 4 super Young-Mills. And by introducing, of course, matrix product states, one can compute beta state overlaps and take closed form determinant formulas, which of course are a manifestation of quench integrability. So there is the notion of quench integrability, which I don't go to go in, but this concerns the dual gauge theory side. And so one of the manifestations of integrability is the fact that we can really write closed form formulas for the CFT data. That is the structure constants of one-point functions. And of course, yes, this is the question that was just answered. One develops integrable quench criteria that apply to the gauge theory side, and one can indeed show that they are satisfied. So we expect this system to be integrable. Yes, much as n equals 4 dual to 2B string theory is. But of course, as I showed you, 2B string theory was known to have integrability, classical integrability, and we would like to complete the picture by showing classical integrability also in the defect setup. This is, of course, again, the D2, D4 brane system, which pertains to the ADS4 cross CP3 duality. Again, we have D branes along D2 branes this time, and we have an intersecting probe T4 brane along these directions here. And the geometry of the probe brane can be shown to be ADS3 cross CP1 in the non-flux case, but also in the flux case, as I will say. And this is the geometry of ADS4 cross CP3. One can really very quickly see why the geometry of a probe brane will be ADS3 cross CP1. This is the geometry of ADS4 cross CP3. One can set these angles in this metric to 0, and immediately these terms cancel, and then what remains is the metric of this. And the same, of course, went through for the D5 brane, but this is a very, very sketch of the DBI, formal DBI proof of this geometry. And yes, this is of course, I have to say that CP1 is nothing but a two-sphere, again. And as I said, we can introduce flux to the system as well in the CP1 or S2 part. And again, D2 branes will terminate a number of D branes. Q, which is proportional to this flux, will terminate on one side of the D4 brane. And the embedding of the D4 brane will be very similar to the one that we saw before, but in a probably more complicated background, which is ADS4 cross CP3. And again, we have the same geometry for the D4 brane. We have a tilted brane in ADS and a CP1 brane inside CP3. And again, this is the setup for the holographic setup that was recently set up by Christensen, Wu, Zarembo, and the recent work by Gombor and Christensen showed that one can also write down closed form determinant formulas in this theory as well. Smoking gun of integrability of the system. And as I anticipated, we want to study integrability on the strongly coupled side of these dualities, namely on the string theory side, which of course entails open strings. And ending on these D-branes that I showed you, having these embeddings that I showed you. And so in general, so the general question is, of course, whether opening the boundary conditions of integrable. So if we have boundary conditions which are closed and unintegrable, and we suddenly open them, is integrability of the strings preserved? And the answer is no, and we already have backgrounds which, even in this setup right here, we have backgrounds where certain non-supersymmetric D-branes are either known to break integrability of ADS5 CFT4. But there is another setup, of course, non-supersymmetric that we don't really know. It might preserve integrability. But we know examples that break integrability. So the question is whether we can still have integrability in these theories. But the signs, of course, are very positive. And yes, and they go after the fact that we have already found, people have already found, worked out closed form determinant formulas. And as I said, there is, yes, what's this? Yes, one can use, of course, the conformal data to solve the theory, yeah. But I want to say about integrable Quench criteria, which I briefly mentioned previously, which, of course, are formulated by means of the parity of charges of the spin chain of the theory, that is, describes the dilatation operator, etc. So if this actually annihilate the boundary state, so then there is a nice criterion by Piroli, Posgai, and Vernier, which says that the quench or the defect CFT seen as a quench, if we weak rotate it, is integrable. And this has been shown, of course, for both of these systems. That, well, recently it was shown also for the ADS4 system. And of course, as I said, closed string, we just show that, seen that they are integrable, and the question is what happens if we open the strings. And of course, there is, I should probably highlight the work of Adek and Oz, which actually proved the classical integrability of both of these systems, which is yet another indication that these systems are integrable, but for zero flags. And my work with Kostya is that we generalized this work to system having non-zero flags on the D-brane. And now this brings me to the topic of D-brane integrability. And but I first have to remove the fermions. So I only consider bosonic strings. And the action, of course, that the string sigma model on either ADS5 cross S5 or ADS4 cross EP3 in the absence of fermions reduces to the Polyakov action. And here we also have a flux on the boundary, which couples to the string action by means of this boundary term. So and one can vary this action.
Sorry, can I just?
Yes, yes.
I missed. Why did you get rid of the fermions?
In order to make my life easier. Okay. It's much more difficult. I can comment on the fermions because, yes, it's, yes, yes, I'll probably mention that later, yes. It's much easier to study, of course, yes, the case, but it would be, of course, an interesting complex question to study the fermions as well. And so if I vary this action, by demanding that the variations on the initial and final states vanish, I can arrive to this result, which says that the boundary conditions, and boundary conditions is this exclamation mark on the equal sign, this holds on the boundary, are Neumann-Dirichlet for the longitudinal coordinates of the string, these, and transverse are Dirichlet. And of course, I can translate immediately this set of boundary conditions. These are all the boundary conditions I can write for this system. And I can make this statement more precise. I can insert the parameterization, the embedding coordinates of ADS5 cross S5, and take these boundary conditions, which I don't know whether they give rise to integrable string motion in these backgrounds. And of course, the same goes true for ADS4 cross CP3. I have these boundary conditions with flux, non-zero flux in here, in either ADS4 or CP3, and I want to know whether I can generate an infinite number of conservation laws, which I can invert and really solve my string, open string, bosonic string. And so in order to be able to answer the question, we need a construction which reminds us very much of the construction we had in the bulk. And this brings us to the work of Sklianin, which defined the double row monodromy matrix, which is built of the monodromies that we used in order to construct the hierarchy of charges in the bulk or for periodic boundary conditions, and a reflection matrix U, which takes the boundary into account. And this, of course, means that, so the charges, of course, you have to see this as, the charges are really, the conserved charges of the bulk are contained in these monodromies, but then the presence of this non-abelian structure in this monodromy, in double row monodromy, really eliminates certain of these charges, and we're left with less conservation laws. Well, we can, of course, have all the conservation laws in certain cases, but formally, we get less. And our task will be to find such a reflection matrix that will allow us to construct the conservation laws from this double row monodromy matrix. And the procedure is the same as before. We differentiate, and we demand that this matrix is constant. And when we do this, we arrive to this integrability condition, this exactly here, that must hold on the boundary. And this transfer matrix will be conserved. And of course, here is just the fixed frame Lax connection that holds for strings in the bulk. And yes, and now yes, I can really because we have, of course, this we can plug this Lax connection into this formula and get a more precise form of the integrability condition, which is this one over here, which contains, of course, one term for boson, two terms for bosons, and two terms for the fermions. Let me connect with the work of Dekel and Oz. Of course, you see that if we include the fermions, we have more terms here. And this is already very difficult to solve, and you'll see that it leads to a complicated solution. But what Dekel and Oz did, they considered the no-flux case. In the no-flux case, this U matrix, this reflection matrix, is really a constant and does not depend on the spectral parameter, which means that this is 0, this side is 0, and these terms are really decoupled from each other, and they can be set to 0 and then easily be solved, even in the fermionic case. But in the bosonic case and for generic U structures of U matrices or reflection matrices, we have to solve this equation, which of course is dependent on the spectral parameter, and in fact U will turn out to depend on both the wall-sheet time, tau, through the coordinates, and the spectral parameter. and of course, the form of the U matrix in the bosonic of the reflection matrix in the bosonic case is just the block diagonal. One part for ADS and the other part for the compact space. And our job, of course, would be to find the U, which we will plug in this formula and make it and satisfy this formula upon using the boundary conditions that I showed you before. And then we can claim that the boundary conditions are integrable because we can really expand this matrix along, for the spectral parameter and obtain the charges as I showed you before. So let me go to the details. The details are that we know the coset element of ADS5, which is this one, and these are the P's and the D's and the K's are just the conformal generators in 4 dimensions. And one can use this in order to get the current and plug the current into this integrability condition and then search for a reflection matrix. And the reflection matrix is just the Deckel laws, constant reflection matrix gamma 3 plus a structure that depends on both the coordinates and the spectral parameter. And that was my work with Zarembo in 2021. And of course, as I said, that the K is 0 case, which K is here. If this is 0, then this is a constant matrix which fits perfectly with exactly the Deckel laws result. And the same goes through for ACE5. The parameterization is given by these nice quantities right here. We know again the current, and we can construct again these reflection matrices which are dynamical. That is, they depend on the coordinates and on time, and they depend also on the spectral parameter. And again, the zero flux case is the Deckel laws result. And ADS4 is very much similar to ADS5, and the reflection matrix is very much similar, and this part was really very, very straightforward. And again, Deckel laws had studied this case for Q equals 0, that is no flux. But of course, the CP3 parameterization is a bit more involved. And that was probably the non-trivial part in this paper. One can construct the charges, which are very much more complicated. But if one plugs it into the integrability condition and looks for a reflection matrix that satisfies it, one can find this reflection matrix here, which is not too complicated, but it works, and it really also reduces to the Deckel laws result for the zero flux. And that was more or less what I wanted to say. The conserved charges can be obtained, of course, by expanding the double row monodromy matrix at x equals 0. They are supposed to be independent, of course, since they are subset of the charges in the undeformed case. And but they are not going to be all of them are not going to be there. And of course, this work also may give rise to interesting other research directions. And so I have put the German version of thank you here. Yeah.
Thank you very much for the nice talk. Questions?
So you have written down these integrable boundary conditions, and I didn't understand if different choices are possible, and if yes, what would be a way to classify the full set of possible integrable boundary conditions?
So the boundary conditions were obtained from the Polyakov action with a boundary term when we vary it. So these are all the boundary conditions that there can be with this condition on the boundary. And these are all. And these are integrable. And Yes, I don't know if so anything that can be written in this way gives rise to this is formally what's the interpretation of this result.
Yes,
And of
maybe
course, this translates to these boundary conditions in ADS and the other, of course, in the ABJM.
Yeah, so for example, take ADS5, do you have other possibilities than what you have written in this slide or not?
There might be, of course, but if one can relaxes this kind of conditions, I don't know. Yes, there might be. Of course, there are the fermions, but if one relaxes these conditions, yeah. But you see, yeah. So formally, we want the boundary. How do we obtain the boundary conditions, right? We vary this action, and we end up with a boundary term, right? Because we have some partial integrations, we end up with a boundary term which has to vanish, actually. And if we set this type of conditions, then this boundary term would lead immediately to this boundary condition, bosonic boundary conditions. Yes. Now, one can ask, can we put some other boundary conditions which will lead to a non-vanishing boundary term? I don't know. Yes. This I haven't thought about it. But, yeah, maybe I need to say something about the fermions, complete the answer. So, of course, the fermions show up here in the integrability conditions. Of course, as you saw, the reflection matrices I got were really complicated. And of course, if one includes the fermions, they become much more complicated. But including the fermions really also modifies the bosonic part of the currents. Usually, the fermions are really, for example, we usually have this bosonic element. The fermions show up with an e to the x, the chi element, right? And then this, when one attempts to get the currents, one finds that there is a fermionic contribution to the bosonic currents. So not only this part will show up, but this part will have a fermionic component, which is bosonic, of course, but it's composed from the fermions. And one can really try it. Maybe I haven't examined this possibility. It would be, of course, very interesting to see if one can solve the full fermionic.
So maybe I have a somewhat related question. Can you just go forward a few? Yeah. So this you have written down in coordinates, right? In target space coordinates.
Yes.
Do you have any idea if there is a form that you can write down that does not need you to explicitly reference target space coordinates or use generators? That maybe then you can generalize, including fermions, more easily. I don't know whether.
Yeah,
there
is the question whether this classical reflection matrix arises from some quantum K matrix, right?
I'm asking a much simpler question.
And this is too complicated. So this part, this dynamical part, is too complicated actually to hope for somebody to really reproduce it in some classical limit of some quantum.
I mean, I think I'm asking a much simpler question. I just want to write it as in terms of G rather than in terms of X's.
In terms of G, yeah. No, well, we didn't. It would be very interesting. Yes, yeah. It would be interesting to actually try to write it. There could be some freedom in actually writing down this the dynamical part, but we didn't really go very much into it. And it would be very interesting, of course, if somebody came up with a simpler form for this, because of the reason also I explained.
Do we have any further questions?
Maybe just to clarify, can you go to the second slide? Sorry, the slide after this one.
The next one, this one?
Oh, no. So
Previous?
where you wrote down the U dot, yes, that's one. Thank you. So can you clarify why taking U to depend on time, that it gives you a boundary condition with a flux? Because if I look at this expression and it's telling me a relation between the sigma component of the current, from the second part that has to be 0, and then from the first part you get u dot and then the tau component of the current.
So your question is why we, for non-constant flux, we end up with dynamical reflection?
Yeah, why taking u dot to be non-vanishing, why it gives you a flux in the Neumann boundary conditions, basically?
Well, it's a fact of the calculus, actually. Dekel knows, well, if one tries, first of all, if one tries actually to solve these equations without a flux, one cannot solve them really. And we tried, of course. That was our initial, we probably delayed writing down this paper because we at first we thought that the reflection matrices would be constants. And so we tried, of course, if this is 0, but still dependent on, you mean if this, if this is not, this is constant, but still dependent on the spectral parameter?
No. Yeah, simpler than, I'm thinking about the generalized Neumann boundary condition, which is a condition between sigma, the derivative of the coordinates with respect to sigma and tau, that it relates those two things. And here I just look at the second piece, which has to be 0 if I expand in the spectral parameter. And so I don't get a relation between a sigma derivative and a tau derivative. So I didn't understand why it would give you a boundary condition with a flux.
No, this is dot, right? This is tau derivatives, right?
Yeah.
And you mean here we have, yes, this should, this should, I think this should independently vanish, or there is some cancellation of sigmas, yes. No, this takes place. But I cannot really recall all the details here. So you mean this, so let me rephrase it if I understood correctly. So you say you have these J sigmas here, which contain derivatives with respect to sigma, of course. And and the question is how I can make friends with this part, which only depends on derivative of tau. And the answer is that this part, well, one answer is that this part, let's see. Yeah, I don't remember very well, but yes. So if I end up, so one part, of course, would be that this cancels independently, right?
Yeah.
And then we still have a derivative here, and we still have all of that. But let me see. Is this all dependent on sigma? I don't remember very well. Yes. Yes. This is a good question, but it turns out that one has to use these matrices that we use, and I cannot remember very well what was the case for this. I cannot remember. Yeah, I don't think there is. Yeah.
We can talk about it afterwards.
Yeah, we can. Yeah.
The question originally is just because maybe probably previous slides you write down the generalized Neumann, which is a relation between the tau derivatives and the sigma derivatives.
Yes.
And so
that's also, yeah, that's also, yeah, you answered the question, yes, indeed. So that could also be, right. Indeed, so the boundary conditions really, yeah, that's the answer, indeed. So the boundary conditions really mix, let's see, where do they mix? So these are primes, but here you see they mix, dot and prime. And so we replace the derivatives in the sigma-dependent part with the tau derivatives, and then this couple with the other part, and they make 0. Yeah, that's a very good question, yes, a very technical question, but it's very interesting. So this couple, and indeed, that's the reason why they cancel.
Any further questions? So we will thank George in just a second, but before, don't run away after we do. So let's first thank George. So I want to keep you here for a couple of seconds, just to make a few. Oh no, what have I done? How do I get back in? Sorry. We will see if I'm good. I don't know. Just remember how to use a German keyboard. And that one. Great. So yeah, maybe I'll take this off. So the first thing I want to say is that last year we were in Santiago de Compostela for the first edition of this InJual Def. This year we've had a very nice time in Berlin, and I'd like to invite you all next year to Durham, where we will hold in Dual Def in the last week of July. There will also be an edition of the Young Researcher School, so be careful. There is the next edition of the Young Researcher School is in Stockholm in October. This will be the following edition, which will be on topics not fully decided, but related to symmetries and conserved charges in classical and quantum integrable theories. So I'd like to invite you all there. I hope to see as many of you there as possible. I'd also just like to take this opportunity to thank all of the, before I hand back to Stein to close the conference, to thank all the local organizers. So we have Khalil, Tim and Yannick, Jenny, who I guess is not around, Rob and the local technical team, and of course Stein. I think you'll all agree with me, they've done an absolutely fantastic job. We've had a wonderful week, and I'd just like to give them a big hand. So back to Stein to close.
Thank you, Ben. Yeah, so I'm going to partly repeat what Ben just said. Yeah, we've come to the end of this week's conference. So I personally think we've had a very nice week here with exciting talks and fruitful discussions. Maybe more so for you guys on the discussion part than for me, because I was running around. But so first, 3 final practical announcements. So there will still be lunch now. And if you don't have to leave, you're welcome to stay here and discuss with participants. You can do it here in the seminar room or upstairs on the 2nd floor over there. There's 2 seminar rooms for you available as well. Then another thing, if you somehow get sick or have to get tested for corona because of flying or whatever, if you test positive, please inform us, and then we can put this on the website in some way, anonymized of course, but just so that other participants know. Yeah, then to be sort of good for the environment, please leave your lanyards here if you're not going to collect them and use them for anything. Right. So then, yeah, I would also like to thank some people. So I'm going to forget some people. I apologize in advance. So first, I want to thank my fellow organizers, so Ben, Mark, Ricardo is here, and Rob is not here. Bad Rob. Anyway, he still gets a thank you. Yeah, so for their big contributions in helping organize this conference, I'm sure without them it wouldn't have worked out in the way it did, or at all. Then yeah, on the practical side, I mean, the Secretary Jenny Collard has been amazing. She's done so much. It's really great, and I want to thank her a lot. I also should thank this Integrative Research Institute for the Sciences that we are in, that I'm a part of, for their help in, say, providing this room and suggesting options for catering, all this kind of stuff. So in particular also Nora Butter there. Yeah, then I would like to thank also Yannick, my PhD student Tim, my PhD student Khalil, and 2 other people, Moritz Kade and Matthias Volk, who are in Matthias's group, who helped a lot with the recording. Of course also the technical people from the computer department here. Then yeah, financial support. I'd like to thank the German Science Foundation, DFG, the Foundation La Caixa, and the IGFAE in Santiago de Compostela, and the DFG Graduate School Rethinking Quantum Field Theory here for their support in organizing this conference. Otherwise, we wouldn't have had food, for example. Yeah, and then finally, I want to just thank all of you for coming and contributing to this stimulating atmosphere of the last week. And I hope all of us will meet next year in Durham. And I wish you all a safe trip home, and thank you very much.